We'll move the lecture along. We got some work to do today. New stuff. Well, not really new stuff, but just applications. So I got a lot of examples for this Newton's law thing. So we introduced Newton's law. We the first and the second law. I guess I didn't technically introduce the third law, but let me go ahead and do that. And then we gave some examples of the first and second law. And then I'm going to go and just basically do a lot of examples. And I have a kind of a favorite set of exercises that I can tweak and derive the solution for to really illustrate subtleties about the first and second law. Blocks on planes in tandem. That's what I call them. But let's formally introduce the third law, and then we're good. We'll go back to all those examples. So the third law is probably the most, well, I don't know. Actually, maybe it's close second, right? Because it's the third law is such a universal thing. It applies. It's really maybe more when we look at the third law, it's kind of a with regard to the laws of motion. You might say that it's like a special case of something that people consider to be more universal. We won't get into that, but the third law specifically states that for every action, there's an equal and opposite reaction. Action in this case means force, in the sense that we're going to be using it. So when you sit down on your chair, the seat of your bottom applies a force to the chair. Now, sure, the earth is attractive force on you, which is your weight, and you then apply a force on the chair. And as we have seen in previous sections, a previous conversation with analogous, like with me on the floor, me standing on the floor, we talked about that a few weeks ago, a week and a half ago. But when you sit on the chair, there's going to be a contact force on your bottom. A normal force is what we call it, and it points up. Now, we can do a simple force diagram to show that the normal force of the chair on your bottom is equal to the force of you on the chair. So that's a nice example of the third law, where you have equal and opposite forces being applied. Now, same thing. If I lean on this desk here, my hand is on the bookshelf. My hand is pressing against the bookshelf with a certain component of my weight. Well, I don't fall. I don't continue to accelerate through or fall through. So something has got to be keeping me from doing that, and it's obviously a contact force, basically a normal force. We can call it a normal force of the edge of the bookshelf on my hand. Now, normal, the term normal, I think I mentioned it, but I don't think I remember writing it. It's normal. It's a geometrical term that means 90 degrees. So a normal force is a force that is 90 degrees relative to the surfaces of contact. And the symbol that we use for it is N. Sometimes you see F sub N in books, but I just use N. So any kind of contact force where you're pressing on something, right now I'm pressing my hands together. The flat surfaces of my hands are pressing against one another. My right hand presses on my left hand presses on my right hand, right? If I were to diagram those forces, so here's my hand, I don't know, I'm not very good at this, but and then here's the other hand. Let's do a different color. Whatever. Two different objects. Hand right and left. So there's going to be a force on the left hand due to the right hand, right? So that's the force of the right hand on the left hand. And this guy on the right hand is a force of the left hand on the right hand. So the third law, you would state it the following way mathematically, that F RL equals the negative of F LR. In terms of magnitudes, F RL equals F LR. The magnitudes are equal, but the directions are two things. So yeah, that's magnitudes equal, directions opposite, and this is a crucial one. This is the most subtle one. So magnitudes the same. Well, let's describe what I'm write down first what I'm describing. These are called pair forces. Pair forces. And pair forces have certain characteristics there, and there are three that I'm specifically pointing out here. One is that the magnitudes are the same. Same magnitude. Opposite direction. And this is the big one that I was leading up to. Pair forces, without exception, are always on different objects. Pair forces, without exception, always occur on different objects. If two forces are on the same objects, they will never be and are never considered pair forces, ever. Let's just say different objects. I don't want to make it too wordy. So same magnitude, opposite direction, different objects. All three of those criteria must be satisfied. Otherwise, these things don't have the possibility of being pair forces. Now, just because they may be satisfied doesn't necessarily mean they're pair forces. But if they're not satisfied, they definitely won't be pair forces. Hope that's not confusing for you. Other nice examples are gravitational force, right? Third law applies to that. If you have a big mass, right, mass 1, and over here mass 2. Now, there's other aspects of gravity, that properties of gravity that we won't talk about now. But point is, if you look at the line through the center of mass, of the objects, let's say that's it. Then on mass 2, you're going to have a gravitational force due to mass 1. And gravity is an attractive force. So in this case, as compared to this compression normal force here, the forces are going to be acting toward one another. But still, they're in opposite direction. So this is F2 or F1 on 2. Maybe I just say F1 just to be so it's not, yeah. And this is F2 on 1. I'm gonna go. That's the convention that we use. I'll stay with that. Yeah, so I can make a similar mathematical relationship between those forces. Those are pair forces. Those are pair forces. Like I said, if you're sitting on your chair, which you are probably, then we could do something like this. We could say, okay, and let's just say a mass. In fact, let me just make a new example so you can see it and visualize. I have a block mass here. Sitting on a tabletop, I'm going to diagram it right here. Mass. Now, we've done this before, so I'll go through it. We've got two forces on it. One is a gravitational force. All forces acting from the center of mass. So the gravitational force is mg, but it has another force on it as well, as a normal force due to the surface of contact between the box and the podium. So those surfaces, that force is acting on the box, the bottom of the box, due to the tabletop, but it is acting opposite the direction of, well, perpendicular to the face of the contact face between the block and the podium. Now, it's actually acting right here at that point. But because I'm not changing the direction or the angle of the vector, I can project it up to the center of mass just because it's convenient. That's all. It's not really acting at that point. Normal forces are forces of contact, so they act at the point of contact. The tabletop does not have contact with the center of mass. So I've mathematically projected this normal force from where it's actually acting somewhere on the surface there up to, or really collectively, in fact, it's kind of a summation, and really, summation of all the atomic forces, things of each atom that's in contact with one another. We sum all that, call it one force, say it's acting, on that surface, but then project it up here to the axis. Well, at least where I'm going to place the axis. And it's just convenient to do that, right? So we can have all the forces acting from the center of mass. In fact, what we're really saying is that we didn't treat this whole object like a point particle, a particle that has no size or shape, but has all the mass of the block. That's really what we're saying. In other words, we could replace this thing with a point particle that has its center mass at that position. I don't like to redraw it and do that because I still like to have the object in mind. And that's easier to do whenever you have, you still have something that represents the object there. But this is rigid body physics, so we basically treat rigid bodies like a point particle with no shape or size and whatever mass is the object. At any rate, the question is, now we know if we apply Newton's first law, and why do we apply it? Because it's not accelerating in either direction. So we know the first law is what applies. I'm going to apply to the y direction. If I do so, the net force in the y direction equals 0. Again, why? Because no change in motion here on the right, on the object. Remember what I told you, the left side of Newton's first and second law are the change in motion or motion side, kinematic sides. The left side is the dynamic side. Not so with the third law, by the way. This is the third law. It's just force equals negative of the other force. So not quite the same deal. But yes, with the first and second law, we have that. Two forces, normal force minus mg equals 0. So this is telling me that the normal force is equal to mg. Okay? So my question to you is, are these pair forces, the normal force and the weight? Karim, want to answer that for me? Are the normal force and the weight pair forces on that example? Why or why not? What happened to Karim? I thought I just saw him. Did he just leave? Okay. Joe Leon, how are you? Are you there, Joe? Okay. Gabriella, are you there?
Yes,
Hi, how are you today?
I'm good.
Good. Is this lecture making sense to you so far?
Um, I'm trying to figure it out, because I wasn't here Monday, but I'm reading the chapter.
Okay, well, that's good. I appreciate that, and that's all good. But I have everything that you need to know for to answer that question I've
Mm,
said here. So
Okay.
you know,
Um, so can you repeat the question?
question is, are the
Mm-hmm.
normal force and the weight pair of forces for this example? I've defined what pair of forces are over here. I'm just asking, are those forces pair of forces? And defend your answer. Why or why not?
I would say yes, because they have the same magnitude.
Okay,
Um,
great.
and I don't know if are they opposite? Yeah, they're opposite direction too.
Yes, right. Okay. So
Mm-hmm.
that's your final answer?
Yes.
Okay. So I'm not sure why it is, which is the reason why I'm asking you this. I'm not sure why it is. I've never figured this out. Uh, every time I do this lecture, and any lecture, it doesn't matter how I present it or anytime I've seen it, the first time that most students, and this is statistically, maybe not all of you would agree, but statistically, everyone leaves out the third option. I don't know why. And I turned around and specifically said it to the camera. Still yet, every time I do this, at least half of the class say that these are pair forces. And I think it's just because I think I probably even did it when I don't remember, but for some reason this has always been kind of a pet, not a peeve, but just something that I make sure I point out because you have to kind of think about it. There's a third criteria here, and I told you that all of these criteria have to be satisfied. So just so we can read it, Gabriella, can you tell me what that third criteria is?
They're different objects.
Well, no. What I didn't write out the full sentence. Maybe I should have.
Oh,
Pair of forces act on. Maybe I should.
okay.
Yeah, that's a
Sorry.
act on different objects. So are these forces acting on different objects?
Yes.
Really? These two forces are acting on different objects. Is what this is the weight. So what and this
Mhm.
is the block M. So what is the object that the weight is acting on?
Um, the block.
Yes, it's the weight of the block. So clearly it's acting on the block. Now,
Mm-hmm.
this is the normal force. And I know that's probably kind of new, but what we've been saying is that the normal force is, well, where you tell me, where is the normal force coming from?
Um, it's coming. It's in the. It's pointing up.
That's the direction,
Mm-hmm.
true, but what is the origin? What is creating the normal force?
The X direction.
An
The
extra direction doesn't
the
create a force.
origin.
Let's back up.
Oh,
I'm going to lean on this shelf. Now I am pressing on the shelf, so there's a force on the shelf, but there's obviously also a force on me, right?
mm-hmm.
Where's the force on me coming from?
The shelf.
The shelf.
Mm-hmm.
Exactly. Look at this box on the table. Now I'm going to pick the box off the table. I guess I can't do it without applying some other force, but if I were to pick up this box and like somehow, let's say this is Hogwarts. This is my little wand here. I wave my wand, the box just floats up. It's hovering there in the air. When it's there in the air, will there be a normal force on it, Gabriella?
No.
No. So when I then wave my wand again and I sit it down on the table, is there a normal force now?
Yes.
Okay. Where is the normal force originating? What is causing it?
The table.
The table.
Okay.
So the force is on the object and it's on the object due to the contact of the table. That's literally what the
Mm-hmm.
third law says.
Okay.
The
Sorry,
object
it just
presses on.
because it just was hard to like see the picture like that you drew with the
Okay,
x-axis and yeah, sorry.
okay,
But I
fair
see
enough.
it now.
Awesome, awesome. Yeah. So again, are those forces then acting? Those are two forces. They are the only two forces on our object, the weight and the normal force. So I ask you again, are those forces acting on different objects?
Yes. No.
Okay.
Then
What? So
no,
what are
because it's just on the table. It's just on the table. So no, it does not act on different objects.
what's on the table?
The block.
The block is on the table, but I'm talking about the forces on the block.
Okay.
Those forces are acting on what?
The table.
So I think you're overthinking now. Maybe it's the way that I'm asking the questions. I don't know. But you already told me once that the weight is acting on the block, which is obvious, right? Because weight is the weight of the thing that is itself. It's well, let's break that down a little further. Where is the weight coming from? What is the source? What is the object that's causing the weight to be on this mass? What creates weight?
Gravity and mass
Gravity. Yes, Hayek. And so where's gravity coming from, Hayek?
from the Earth, Earth center.
Yeah, from the center of the earth. That's what I've just illustrated here. So the weight is the force of the earth on the mass, right?
Yeah.
Okay. So the answer that I was looking for is that the weight is originating because the earth is applying a force on the mass. So this weight is definitely not on anything else but that mass. And it's coming from the fact that the earth is applying a force on it. Hayek, the normal force. As we were just saying, the normal force is coming from the tabletop. If there were no contact between the block and the tabletop, there would be no normal force, right? Just think about let's make it physical. Let's throw in another sense. As opposed to just your vision, let's throw in the sensation of your body. Many of you may be sitting down right now. When you're sitting down, don't you feel a force on you from the chair? When you stand up, you do. When you stand up, is that force there?
No.
No. Well, that force that we're talking about, that is the normal force. That's the name of it. That's what we're calling it. So when we take that example and bring it back to this object, the answer that I'm looking for is that the normal force is coming from the tabletop. And it is not on the tabletop, it is on the block. It is the force of the tabletop pressing on the block, just like you have the force of a chair pressing on you when you're sitting on it. So the answer that I was wanting is that both of these forces are on the block. They're coming from two different things. One, the weight, the center of the earth, the normal force, the surface of contact between the block and the table, but they're coming from two separate objects or two separate, phenomena or objects, I guess, interacting in some way specific to their characteristics to the block. But the forces are on the block. So these two forces are on the block. So Hayek, how does that classify them in terms of the criteria of pair forces? Would you say they are pair forces and justify your answer?
Well, I wouldn't say they are pair forces because you've told us it's acting on one object. So, but the forces are different directions, have same magnitudes, but act on one object. That's why they are not pair forces.
That's the answer that I'm looking for. they are not pair forces because they're acting on the same object, as you said. And one of the criteria for pair forces is that they always must be acting on different objects. That's what we see in the examples that I gave. In my hand, I have two hands. One force is on one force is on the other. Sure, the other two criteria are satisfied for this object, for all of them, but only for these two scenarios is the third criteria satisfied. It is not satisfied for this. So even though those forces are equal and opposite, they are not, they are on the same object, so they cannot be pair forces. Okay, does that clarify? And Gabriella, does that clarify that for you?
Yeah, sorry.
No, don't apologize. You don't need to apologize. You've never seen this before, so you wouldn't necessarily know it. It's okay. Don't feel bad. It's a learning process, right? So I don't mean to. I would hope that I wasn't coming across as critical. And that thing I said early on about it wasn't. It's not a criticism. It's just an observation. It's kind of like I'm from South Carolina, and I left home years ago. I've probably been away from home for almost 30 years now. And I kid you not, everywhere that it doesn't matter what state I'm in, no matter where I am, whether it's the South, Midwest, out here, the West, go up to Northwest, even the Northeast, when I meet someone, and we're kind of casually talking, I might say, they say, where you're from? And I say, oh, I'm from South Carolina. Just casually like that, without fail. Somewhere later on in the conversation, if they reference where I'm from, they always say North Carolina. I don't know why that is, but it consistently happens. So I think I don't know, maybe something, I don't know what it is. I don't know I'm not a psychologist or a sociologist. I don't know. But I think it does have something to do with the way that we process or socialize certain things. And this is one of those things. Like, and it is a little bit tricky too, right? I don't know, whatever. But that's the last criteria. You always have to put that in. So keep that in mind. So let's move it on. So the other thing I want to say is that kind of universally, what all of these characteristics imply is that forces, without exception, always come in pairs, which means that there's an equal number of forces in the universe. And anything other than that would be a violation of a lot of principles, conservation of energy, a whole lot of stuff. But I mean, that's just a simple thing, but that's kind of like, I think that's significant somehow. I don't know how, and I don't know any kind of law that has exploited that or talked about that, but maybe because we're still evolving and still understanding something about the universe. But I think, that's really significant. Because in physics, we're going to talk about something, maybe not so much in this class, but you might have heard like advanced physicists and people talking about breaks in symmetry in the universe for various laws. So as I told you, symmetry is, a theme of the course. So it's something we look for, and we somehow the universe it's quite symmetric. In fact, that's an example of symmetry in a much larger picture. But just like artists like to look at the negative space and evaluate that when they're drawing a picture, particularly in black, still photos in black and whites and things, but just in general. And you can just by mapping out the negative space, you can make a whole silhouette of an object. There have been many great pieces of artwork that have exploit that kind of idea. So that's also a symmetry of the universe. And so physics is that way as well. So maybe looking at breaks in symmetry is kind of a way of looking at the negative space in a sense, to make an analogy. So whenever there's a break in symmetry, physicists are all over it. Like, well, it's breaking symmetry. Why does the universe do that? So the idea that all forces in the universe come in pairs, implying a symmetric function, even function, is well, symmetric doesn't necessarily mean even. Sorry, odd functions can also be symmetric, but just negative. So maybe this is an odd function because the forces, they're pairs, but they have to be negative. I don't know. I've never thought about it. It just occurred to me just now. Yeah, maybe that's true. Maybe it would be, I don't know what that means, but I just think it's quite significant that that's the case. Is it Mikey or Mikey, I guess, right? Not Mickey. Mikey.
Yeah, it's Mikey.
Yeah, go for it.
This might be kind of a dumb question, but it's kind of killing me right now. How come the a normal force in the diagram, it looks like it's 180 degrees from the other force, not on 90, but I think I might be visualizing it wrong. Or just not in the way that like it makes sense to me, I guess.
You're visualizing it. Maybe the way that I said it might be confusing. I don't know. It's a normal force. It's 90 degrees relative to the surface of contact. The surface.
Okay. Oh, I see. Okay.
Yeah, but you got a good point because we haven't yet because that's in the EM. Yeah, so the surface, is flat, right? It's like horizontal, and for both of them. So if I were to, have an angle, like a force that's relative, because it's pushing, even though the surfaces are flat, it pushes up. So the normal force is in the direction of the push, if you will, if you're thinking about it like your bottom sitting on a chair. And that's going to make a 90-degree angle with the surfaces, the contact surfaces. Does that make sense?
Yeah, that's what I thought it was, but like I was kind of second guessing myself, so I just wanted to make sure.
Yeah, it's okay. It's okay. Yeah, and maybe I could emphasize that here. Maybe I could just emphasize it here that it's 90 degrees relative to the horizontal, keeping in mind that the surfaces of contact is along the horizontal, namely the x-axis. Where is it? Here. So it's 90 degrees relative to that surface. And here is the surface here, so it'd be 90 degrees relative to that too. Okay. Cool. Any other questions? All right, wonderful. So we did the static situation, hanging on tension. We did thing rolling down the plane. So now we want to start to put things together. So let's say that I have a mass and it's on an incline, well, actually on a flat surface. And I take something, a ball or something, and I attach it to that mass. And so naturally what's going to happen is, I don't know, give me a little, maybe. Now, just assume that my surfaces are frictionless or that I have a pulley or something hanging on there, which I don't, but assuming that I did. Let's see. So blocks in tandem meaning connect together through a string. And we're going to assume that the string is massless. So I attach this thing on and it pulls it over. Okay. Look at that. So no friction here or anywhere as it attached. This both masses M1, M2 start at rest, and the hanging mass has a gravitational attraction on it, which is translated through the string and pulls it over. Now, you observe this motion a couple times. Let's do it one more time. Would you consider that to be constant motion or accelerated motion? Anyone? Awesome, accelerated motion. As the objects were moving, they started at rest. Well, first of all, if they were constant motion, it probably wouldn't move. But once it starts moving, it had to accelerate at least on some infinitesimal distance. So if nothing changes, it's going to continue to accelerate. So yes, it's accelerated motion. And if you observed it, if I made it longer, you could clearly see that it was speeding up as it fell over. Accelerated. Just like free fall motion, right? We know that's accelerated motion. Accelerated motion. So we have objects on a plane, a flat plane, so relative to the horizontal, the angle is 0 of the plane. So let's diagram that situation and then let's evaluate it, because what we can do is apply Newton's laws to determine the value. If we know the mass of each object, and we know the plane angle, we can determine several things. We can determine the acceleration of the system. We can determine the tension force in the string, and we can also determine the normal force. Let's do that. Oops. So then that's the third law, by the way. And I think I did review all the forces the other day. This is normally where I do that. But the 4 forces, we've got 4 known forces in the universe. Tell me, I wrote that down, right? Gravity, electromagnetic, strong and weak forces of the atom. I mentioned that, right? Anyone? I didn't write that down the other day. Okay, maybe I'm confusing classes. So why don't I just write that down and say a word or two about that before we do the example? Universal forces. There are only 4 known forces in the universe. Those forces are gravity, electromagnetic, and we know these two because we deal with them. Gravity, obviously. Electromagnetic, electromagnets or magnetic force and electrostatic force, static charge. But those forces are connected. We know that through electromagnetic theory. And you can prove that by, but yeah, they're combined. We'll talk about that next semester. And those are the ones we kind of interact with consciously, mostly. But there are 2 other forces that we know of: the strong nuclear force and the weak nuclear force. Now, I'm going to say something, just my little caveat here. See how specific these names are? Gravity, electromagnetic. And before we combine the 2, it was electrostatic, magnetostatic. Very specific names. Anytime in physics, you've got a vague name like strong and weak, what I've seen is that means the full story is not quite determined. So yeah, but that said, there are conventional models that we assume to be correct, and within the constraint of constraint, of those models, that's what I teach and that's what we talk about. That said, does anyone know what the strong and weak forces, how they originate in the nucleus, in the atom? In fact, I shouldn't say new. Is it strong and weak atomic? I think it's nuclear. Strong and weak, whatever. I think that's what we say. But does anyone know what those forces are and what they're applied to within the atom? In fact, I might be
I'm not
misnaming
sure if
that.
I'm right, but I think like
Go
my
for it.
first, I don't know. I'm just gonna get a job. I think
Go
it
for
might
it.
have something to do with how like for example, if you have like 2 atoms, like their nuclei like may be attracted to each other, but I'm not so sure about that. I don't know if it's even right or how it even like originates. But I've heard about this before though, like that's for sure.
Cool. Well, good try. Good try. It is definitely associated with some kind of attraction of of protons, which are in the nucleus. So definitely associated with the nucleus, but not exactly what think, what you said. Yeah, so you could use, it's either strong nuclear force. You can, people use these words interchangeably. Probably from my personal preference, atomic might be better, but I knew that I wasn't getting that from just pulling it out of the air. So you see both, or sometimes you just call it. They just call it the strong force without a qualification of nuclear or atomic. Strong interaction or weak interaction, or strong force or brute force. All those words, phrases are valid. So you know that now hydrogen is not a good example because it just has one proton in it. But you know, like the Bohr model is that in the nucleus you got protons, right, positive charges, and you got usually an equal amount of neutrons. And then you got electrons, you know, out here around, and they don't really hover around like, you know, like that. Well, we say they don't move around like orbital things, but whatever. I'm not sure we actually really know. But that's the going thing, is that it doesn't really do that, but it does it in a much more funky way associated with things that we won't talk about right now. But the electrons on the outside, the protons and neutrons, like, you know, outside, and the protons and neutrons on the inside. Now, the whole atom itself is only 10 to the negative 10. The diameter, I think it's not nucleus, it's atom. The diameter of an atom, the average diameter is nuclear diameter, not radius. I think is 10 to the negative 10 meters, which is an angstrom. Which means that these protons are so close together, it's impossible to imagine. It's impossible to imagine how close they are. I mean, we can imagine 10 to the negative 2. That's a centimeter. 10 to the negative 3 is that little thing. That's a millimeter. 10 to the negative 10, I can't imagine. And 10 to the negative 10 is this distance, okay? Because the atom is the whole thing, the average diameter of an atom. These protons are all bunched together down here in the nucleus, and they have positive charge. Now, you saw a few weeks ago, 3 weeks ago, when I got a piece of rubber and I took a big old piece of paper, which God knows how much mass compared to a proton. A proton's mass is 10 to the negative 27. This piece of mass of this piece of paper here is probably 10 to the, so it's probably like 0.3 or 4 grams. So that's 10 to the, if it's, you know, if a gram is 10 to the, you know, 1,000 times less than a kilogram, then this piece of paper is at least maybe 10 to the negative 5, 10 to the negative 6. If I stripped it off, 10 to the negative 6, I'm just guessing, 10 to the negative 5 grams. This thing is 10 to the negative, has a mass, mind you, of 10 to the negative 27. Now, that's really about gravitational force, but I don't really have anything else to compare it to, not really, because the paper is neutral. But I'm just saying that if you think about like an ant picking up something that is much bigger than itself, that isn't even remotely comparable to how small this proton is, or a series of protons, no matter how many they are, right? Because, you know, you got more if I rubbed across the carpet and took off a proton, or an electron, you know, rubbed off whatever. Even if I got a few, it's still like very light compared to the mass of, you know, of a piece of paper. And when I brought that, and I know this is not gravitational force, this is electrostatic force, but still it's the electrostatic force of a thing compared to some other thing. When I brought that paper too close to the charged portion of the glass or whatever it was, the thing snatched it up at least 2 or 3 centimeters, like boom. All right. So that's, and the paper was neutral, which means that in the paper, it was basically pulling the electrons because the paper's, it's an insulator. So the polarization effect was happening. I described that to you the same way that you take a balloon and you stick it on the wall, right? Like it's pulling the negative charges close to be affected or whatever, I guess the negative charges might be pushing the electrons away so that you can get that polarization effect and they can connect the charges, bound charges in the surface of the materials. So that's an example, of how strong the electrostatic charge is. Because really, the pieces, what I'm getting at is when we talk about a piece of paper, we're talking about basically atoms, but the atoms are a whole bunch, are lots of protons and neutrons, right? And the electrons, but most of the mass of the paper are the protons and neutrons of the atom in the paper. So when I get a few static charges that exist on a glass or whatever, okay, that's protons as well, but they're attracting how many thousands, hundreds of thousands of protons that are in the paper itself. It's just snatching them to them. Now, it's Coulomb charge and it's working against mass, so it's working against weight, but still, these protons in the nucleus, in the nucleus here, their weight, there's only a few of them, or how many ever they are. They're never going to be more protons in an atom than there are in a piece, in something like a piece of material, because the material is a whole bunch of atoms which have protons in them. So I guess what I'm trying to get you to see is that those few positive charges, and I don't know how many they are, right? It depends on how much electrons were stripped away or whatever, but they would still, whatever the amount of charge that's causing the object to be charged, those number of protons or electrons are excess electrons or protons or positive charges. And remember, the excess positive charges is just the absence of negative charges. But how many ever they are, they won't even remotely compare to the amount of the object, in the object that it's attracting. So in a nucleus, you have a few of those. So the question is, why don't they attract one another? Or I guess in this case, repel, because they're so close, and that's how strong the force is. They want to repel. But if that's the case, everything in the universe would just disintegrate. Just kind of like in the movie, what's the Marvel movie where that dude Thanos made everybody, having people die, and then you saw that. That's what it would look like. That's what it looks like when atoms disintegrate. It's just right. So it's so much force and energy inside this. What keeps them together? Well, again, I'm not sure that we completely understand, but what we say is that there's something called a strong force, and it keeps it together. So there you can see the vagueness of that. What is the strong force? How does it work? I'm not sure the book is completely written on that. In fact, it isn't. But that's what the strong force is. It's basically the force that keeps protons from bursting out away from the atom, specifically given the fact that we know that like charges repel, and that these charges are so close to one another that there must be an extraordinary amount of force holding them together, and there is. That's what the strong force is. Now, that said, the weak force. The weak force, we can make a similar argument about the electrons. Again, this is 10 to the negative 10, 1 angstrom. So the difference between the surface of a nucleus and, the nearest electron, it's not very far away. Certainly much farther away than protons are to themselves within the nucleus, but relatively speaking, not far away, especially when you consider, again, going back to the example, whenever I had charged particles that were attractive, because of polarization and the effect of the static electricity, you're talking about 2 centimeters apart and just snatched it up without a problem. So why don't these protons cause the electrons to collapse into the nucleus? They're so close together, they're oppositely charged. Like, what gives? Well, that is the weak force. The weak force keeps the electrons in their energy shells and their states energy states, well, it keeps the whole atom in a state, but keeps these electrons, you know, in their relative states. Now, you can become excited. Atoms can become excited where they get energy from the outside and causes the electrons to jump outward to a higher state, or even jump all the way out of the atom. But you will usually don't see something causing it to go in to a lower state, unless it's going back to a lower state, which was what its normal state was after having jumped up by getting excited from some energy. But I don't know of any circumstance where an electron is in its lowest state of energy, but then goes to a lower state. When that happens, we're talking about external forces causing things to maybe break the atom apart, and we get stuff like fission and fusion and bombs and all other kinds of things like that. But so the thing that keeps the electrons from collapsing into the nuclei is called a weak force. So that's a quick, more thing, obviously a lot more to say about it, but just as a quick introduction, that's, I think, a good definition of those forces that you probably have heard about, strong and weak, but probably had not done much reading or known much about them other than just hearing about them. Okay, so all the other forces that we're going to talk about: normal force, contact force, any other kind of contact force, drag force, viscous force, friction is a big contact force. All those forces are essentially combinations of these four forces. But because we don't want to get all into the nitty-gritty associated with those, as I said, some of which we don't even understand yet fully, we kind of collectively, macroscopically look at the macroscopic impact of those contact forces on our ability to negotiate, our world, and we call them things that help us understand their macroscopic impact. So when I'm leaning against something, I don't want to. Essentially, what it is the reason my hand doesn't press through the other hand is because the atomic forces, well, not these forces, but the bonding forces of the molecules, which are related to that, but not those forces. We describe them differently. They're so strong that they keep the atoms from allowing anything to penetrate it. So that's why you can't walk through a wall, normally speaking. Now, that said, I think we had a little conversation about that the other day, where I think one of the things that we see with this new movie out, like the Flash, is that he can vibrate himself and walk through a wall. Might be some truth to that in terms of from a theoretical point of view. But that's because the vibration causes, maybe because all the molecules themselves have vibration, right? They have a natural vibration. And when things start to get close in vibration, they can kind of see one another and interact in ways that they normally wouldn't have. So I don't know, it would be complicated to kind of see that and still have atomic continuity as you walk through. But I don't think it's unreasonable that things that are on the quantum level behave in a way that don't behave, that seems strange to us from a macroscopic point of view. So maybe. But unless you can do that, you're not going to be able to walk through the wall, because the molecular and atomic forces are going to be so strong to prevent those objects from interacting in that way. Okay, so that's the four universal forces. Oh, one other last thing to say, but I'll make this quick. The thing that Einstein was working on for his last, 30 years maybe of his life was something called grand unification. I don't think they call it that much anymore. Right now, the going term, I think, is the theory of everything. But initially, grand unification, meaning because these forces initially were all separate forces, we thought. But ultimately, someone proposed, I think Einstein or maybe someone before him, right? But around that time, that especially because there used to be 5 fundamental forces. We used to think that electricity and magnetism were separate forces prior to around 1860-ish, 1864, I think, when James Clerk Maxwell basically discovered light and created electromagnetic theory. When he did that, we found that the magnetic force and the electrostatic force were kind of two ends of the same thing. And you can see that when you create an electromagnetic wave. So whereas there used to be, and actually, I guess at that time, there are only three fundamental forces, because at that time, we didn't know about the strong and weak nuclear forces. So I guess we went from three forces, gravity, electrostatic, magnetostatic, to two, gravity and electromagnetic. And then about 50 years later, we had to throw in, or 50, 60, 70 years later, we had to put in the strong and weak two on gravity and electromagnetic. So I think that's really how it panned out. But as I was saying, then was proposed that since we were able to combine electromagnetic and magnetostatic, electrostatic and magnetostatic into electromagnetic, maybe we could combine everything else. Maybe that all these forces, we're just seeing it from a certain perspective, but in fact, these forces were different aspects of a larger universal God force that is ultimately the force that, if we could figure out what that force is, we could solve a differential equation for it and basically solve the Big Bang. We could determine why things have spread out in all the universe, everything, and everything means everything. It's not just talking about the physical universe, it's talking about consciousness. Everything means everything. That one force, you could derive and understand and predict even everything. Any action, thought, physical, motion, force, everything. But if you just focus on mechanics, certainly all the mechanical aspects of the universe. And since these are only forces that we know of, we assume that if we could combine those, we'd get it. So people started trying to do that. I think probably starting in the late 50s, early 60s, I forget the order, but basically at this point, we have a connection between these three. We have combined basically electromagnetic, strong nuclear, and weak nuclear. The big holdout, which is kind of ironic because that's obviously the first force that we actually interacted with and knew about in the earth, on the world, as a species. The big holdout is gravity. The one that we first knew about, obviously, and the one that probably seems to be the most familiar and the easiest to understand, is actually the most difficult to understand, because we've not been able to combine it with, with the other three. And there's other things out there, like the whole dark matter, which is supposed to be some gravity, in the galaxies that we can't see. And of course, there's dark energy. Now, those two problems are supposedly separate issues. I personally think that they're combined in some way, but that's a different conversation. But the point is, there's a lot of more practical problems that we have, like huge problems in physics, that probably are related in some way to, certainly dark matter is, to our inability to combine gravity with the other forces, which implies that there's much about gravity that we don't actually know. And it's not even that we don't even know what it is that we don't know, right? So yeah, this is what we mean when we say universal forces and fundamental forces. And in terms of our knowledge of forces, this is where the conventional wisdom of where we are in terms of our understanding of these forces. Any questions about that? Okay, so let's bring it back to a more practical application, and so we can learn how to work basic problems. And we'll leave that conversation for another time. So diagramming this situation, let me remind you what it looks like again. I have a mass 1 on the tabletop, mass 2 hanging on a tension rope that's massless. So it doesn't contribute at all to the motion. It just redirects one force over a different, into a different direction and causes the system to accelerate. The system being the string, well, the two masses connected in tandem. So if we were to take a look at that, we've got something like this. I'm going to put my pulley here. Now, also, the pulley is an ideal pulley, meaning it also has no mass and no friction. So it's not contributing to the motion in any way. So basically, it's just redirecting the. No, there's no EM pulley. It's just, or is there? Oh, that's embarrassing. Is there an EM pulley? There is, isn't it? Yeah. Or no? Oh, wow.
I think there's
Hey,
an
Siri. There's an E. How do you
There-
spell pulley?
I think so. I don't think. Yeah, I'm pretty sure the spelling you have up there is the correct way.
All right, cool. Yeah, because I asked Siri how to spell pulley, and she said P-O-O-P. So clearly she didn't understand. Yeah, that's pulley. That's right. It does look right. I don't know. Sometimes things look funky on the board, but that's it. Yeah. So, eventually we're going to have to know details about the pulley. We're going to have to know the mass and the radius, but that's not until a couple chapters, three or four chapters away. So right now, just all you need to know is that this pulley just redirects the force over. It doesn't contribute in any way. So we've got mass 1 over here on the table, and we've got mass 2 down here driving the system, essentially. And our pulley is mapped over the surface like this. Okay. Now, let's also assume that the surface of the table is frictionless for now. We'll put in friction early next week. Frictionless surface. And so that's our basic setup. Now, we know that the system is accelerating. If we look at this block, it's accelerating to my right. I have to establish a coordinate system. Now, I'm going to establish a coordinate system. And I'm going to put it back at this point, but it's, like I'm going to first draw it through the center of mass of this object. But I want to emphasize that it is a stationary coordinate system. It's not moving. It's not pinned to the mass of the object in any way. It's just, I'm going to put it there for convenience because here through the center of mass of this object, because I want to draw all the forces from that position. But this coordinate system is fixed. And I have a little bit, you have to use your imagination for what I'm about to say here. But sometimes it can be a little bit. There's a couple ways you can handle this. I like to handle it this way. Some people start down here and put the axis here. The original one, I'm gonna put it there. But still, we still have this. All right, so that's the axis. As this thing moves, the axis is going to stay there fixed, and we can still evaluate the motion relative to. Now, there's a force, a tension force, basically on the block here at the corner. But again, I'm going to translate that tension force. I mean, I can put it there, but yeah, I'll do it here for now because I'm going to draw a free body diagram. And from the free body diagram, I'll make all of the forces from the center of mass. So we've got 3 forces on this thing. Since we have a frictionless surface, we don't have to worry about friction of the object, the surface of the box on the table. But we've certainly got a tension force here, the string pulling the box over, otherwise it wouldn't move. We've got weight of the object which from the center of mass is acting down, M1G. And we've got a normal force, the force of the table on the block. So 3 forces. 2 along the y direction, 1 along the x direction. Now, I could probably call this tension 1. In fact, I'll do that right now. Tension 1. And then I'm going to make, of course, there's a tension force on block 2 here. And the only other force that block 2 has on it is the weight of block 2, which again, from the center of mass, M2G down. The first thing that I'm going to say here, now, when we're doing problems, I like to break it up into information to explicit, implicit, that sort of thing. Also, I guess we could technically say that block 1 is accelerating to the right, so we could call that A1. A1, so I'll make that over here, A1. Put it here, in that direction. But also block 2 is going down. We call that an A2. But there are certain things that are implied or observed if you look at the situation. One, when you look just from your intuition, and of course, if you did some measuring, you would verify this, these things are connected. And as long as there's no tension in the string, as long as there's no slack in the tension, of course, there has to be tension in the string, no slack in the tension, it kind of looks like these things are moving, at the same velocity at every point, which means if the velocity is changing, then they also have the same acceleration. And that would be correct. Actually, not the same velocity, the same speed. Sorry about that. So we can assume that A1, my first equation, it's going to be an implied equation that the acceleration of block 1 magnitude equals the magnitude of the acceleration of block 2. And so I'm just going to call that a system acceleration, or just A, the acceleration, the magnitude of the acceleration of the system A. So the accelerations are the same. That eliminates an unknown. And I can say the same thing for an ideal pulley. Now, the point of a pulley is to make it easier to pull things. You have a block and tackle system. That has to do, as it turns out, with just the fact that the pulley has certain radii and mass. For an ideal pulley, it's useless. It doesn't do that. So technically, if this were a real pulley, the tensions on either side of the string would be different because they would be the pulley. And again, by the third law, I'm not drawing it here because I'm not worrying about the pulley. But by the third law, the pair force for the tension here is actually up here on the pulley, again, on different objects. And the pair force for T1 is right here coming out the pulley in that direction. But because the pulley is ideal, all these tensions are the same value. They're all T. And that's the point I'm trying to make, is that T1 equals T2 just equals T. The tension force is the same for both objects, and that's because the pulley, like as the pulley is kind of like, we do frictionless surfaces. Ideal pulley is kind of like that. Mikey, question.
Yeah, is it correct to say that T is like the tension force is normal to the weight of mass 2?
Okay, great question. Awesome question. You see, that's really good, Mikey. You're seeing the symmetry and kind of how the tension force looks relative to the geometry of the object. So good, but the answer is no. And the reason why is this. Technically, we consider a contact force something where there's significant contact. So like when you put your hands together, you can feel one hand on the other. It's not just some little point, but there's a lot of surface mass there and there's pressure all over the hand. Same thing when you press against the wall or you sit on the table. technically speaking, you might say that there's something like that occurring right at the little contact where the tension is holding on to the object, and particularly in both cases. But the surface area of contact is so small that it's not really providing a pressure kind of force on the thing in a way. So we give that kind of contact force a very specific kind of name because it has specific characteristics, and we call that a tension force. And that's not the same thing as a normal force. So technically you might say, well, yeah, it kind of, but it's, I see where you're going with that. And I guess I somewhat agree. But we don't want to confuse a tension force with a normal force the way that we're defining them. Because, and the distinction is that if you don't have a large area of surface of contact, but just a small point where the force is in contact with the string is in contact with the surface of the thing that it's holding on to, we assume that that's negligible. We call it a negligible force. And the tension force is really arising in the molecular structure of the string, right? Because let's think about it this way. If I cut this string right here, this thing is going to start to fall. So the mass is going to pull whatever the portion of the string that's on the string is going to pull it down. And at that point where they're in contact, there's still going to be some force there, right? Based on how fast the object is accelerating. So whatever force that is, it's there before and after the string was cut, but it didn't keep the string from staying there once the string was cut. So it must not be the force that's keeping keeping the object in place before the string was cut. Does that kind of make sense?
That's actually a very good analogy. Like, yeah, like I think I know exactly what you mean, actually.
Yeah.
Because if there was an equal and opposite force when like the string is cut, then like I guess the box wouldn't really like fall.
Yeah, we just hover there, right?
Yeah.
Yeah. Right. Yeah. Good.
Because
good. Awesome.
Yeah. So yeah, it makes sense.
Yeah. So really, tension forces come from the cohesive molecular or atomic structure in the string. It's because it's being stretched apart, right? It's being stretched, but it's not giving. So that's the thing that's really causing these objects to be in tandem like that. So that's the difference between a normal force. It's not a force of contact. It's really an elastic force, essentially. That's not giving at all. And elastic force is a specific kind of force that we'll talk about. It's depend on how much the thing stretches, but if it doesn't stretch at all, basically we kind of call it, or negligibly, we just say it's a tension force. But it is actually stretching. It's just so negligible that we don't, whatever. Yes, all right. Our break is about to come up. Yeah, 5 minutes to 1 o'clock to 2:30. Yeah. So let me go ahead and set this up because I want you to work on this during the break. Good. So yeah, so we got that. So that's the difference. That's a great question. Who was that? Who was that speaking just now? Who asked me the question? That wasn't you. Armand's got a question, but who was that?
Oh, that was me. That was me, Mikey.
Oh, Mikey. Yeah. So good question. Armand, what's your question?
Are the tension forces on the string pair forces?
That's a great question. That's a great question. So again, so you mean like at the ends of the string here? No. I wouldn't say that they're pair forces. No, I would say that the pair force of this guy is this one over here, and the pair force of this guy on the opposite end of the string is this guy right here. Because think about it. If I cut this mass, then both of these forces disappear. And yeah. And also that's kind of logically kind of mapping it out. But even just based on the criteria and definitions I gave you, the tension forces here on the two ends of the string, if you want to think about it like that, are on the same object. So they can't be pair forces. But if I cut this portion of the string right here, then both of these forces disappear. I guess these would too, but maybe not. Maybe there's some they would change in magnitude, but significantly, but there might be still a little bit of force there because of some. I mean, if it's ideal, it wouldn't. But if there was actually a real object, there might be some frictional forces on here causing some very small negligible force there. But over here, these forces would be zero. So clearly, these two are not necessarily connected. In fact, they're not. It just looks like it here because when we get to see the pulley as when we see the pulley with a non-ideal situation, these two forces here and here won't even be the same value. So that's another reason that they wouldn't be pair forces, because they won't be the same value. But no matter what the magnitude of the mass of the pulley, when you look at the two on either side, that force will be equal to that force, and that force will be equal to that force when we get to a non-ideal pulley. So for those reasons,
according to Newton's third law,
these two forces are Newton's third law. Yes, okay. These two forces are Newton's third law, but these two forces are not Newton's third law relative to one another.
Okay, so all the ones that you said are consistent with Newton's third law are in opposite directions?
Yes, the force on the mass here arises from this side of the string, being attached. Basically, this force, you can think of it as the string, as a ball putting a force on the pulley or the string on the pulley at that point. And this force is a force of the pulley putting a force through the string on the mass here. So these forces are equal and opposite. So that's why I initially had labeled them 2 and 2 and 1 and 1. Now it gets a little bit confusing, I guess, when you erase that, when you're considering the ideal case. So obviously here, these clearly can't be pair forces because they're not in the same magnitude, right? The only reason you're asking me that is because when I erase them, it kind of looks that way. But that's because this is an ideal situation. This is never going to happen in reality. This is like a freak on the surface will never happen in reality. But it's a great question, actually. It's a great question. And the reason I'm saying that they will never be pair forces is because of they're arising from two different sources, essentially. And for other reasons, because they're on the same object, because they're generally different magnitudes. So generally speaking, all the criteria of pair forces will be violated when I relax the criteria that I'm using now, that this is an ideal pulley. So it wouldn't even be something that you would think to ask if that were the case. That makes sense?
Yes, thank you.
Those are great questions, really great questions. It means you all are thinking about this stuff, so I appreciate this question. Now, last thing I want to say about the third law. Whenever I ask, I will, from this point on in a lot of these problems, and really from this point on, at least in this class, there are going to be other theories that we're going to use to solve things: conservation of energy, conservation of momentum, linear momentum, conservation of angular momentum, other things that we're going to do. Even in that mathematical problem, I've gone through in the one of optimization. I've written it up for you. I'm going to post it on probably a better, more clear explanation and post it on maybe last week's module. I'll make an announcement whenever I do that. But it occurred to me that even in that problem, there are two unknowns. One was the time, and one was the the minimum distance of the space between those boats. And I told you, like, when you get to step 6 in the problem-solving technique, you always need the same number of equations as unknowns. Generally, we get those equations from, physics concepts or trig concepts or something. But in that case, it's actually a process. Basically, you're finding, even though the boats are constant, the velocity of the boats are constant, the speed or velocity of like if you were to look at the space between them, that's one, that space is rotating and it's changing its value to a minimum value and then expanding again. So it has its own angular velocity and linear velocity. If you think of the total velocity as the space in which it contracts and then expands as the boats are passing. And so the two equations in that case is the position equation, the actual initial length of the thing. But then you take the derivative of it, and that's like the velocity. So you get those two equations there. So I kind of got off on a tangent there, but my point is that ultimately, it's this process where we're taking these unknowns and we're going to set up a system of equations and solve them. And in this case, we've got two unknowns, the tension and the acceleration. The system tension, basically we had like 4 unknowns, but these technically are 2 equations that eliminate the other two unknowns. We had 2 tensions, T1, T2, and eliminated in terms of 1. And technically speaking, theoretically, there's 2 objects and they have their own separate accelerations. So technically 2 separate accelerations there. But because of just symmetry and the way that this system is kind of situated, we can call those accelerations 1 acceleration as well. So it reduces the 4 unknowns to 2 unknowns. And the 2 equations, actually there's another unknown as well. There's a normal force, but that's in a different direction. But basically, technically 5 unknowns. And so we need 5 equations, separate independent equations to solve for all those. These are 2, which are trivial. And we've got 3 more that we've got to get. And we'll do that right now. So the point that I was making is that from here on out, even if you're using other methods to solve for a problem, in the case of that math problem, we used a math concept, optimizing, taking the derivative, setting equal to 0. Technically, that gave us the velocity. So it didn't really come directly from a physical concept, but from a mathematical concept. The fact that the derivative of the position vector, the length between the boats per unit time, is a velocity, some kind of velocity. What velocity? In that case, the velocity in which the space between the objects was decreasing and then increasing. It's not happening at a constant rate. That's why you could have a maximum velocity, a rate at which that's happening, and a minimum distance in which that occurred, and the time. But it's always good at this point, whenever you have all the forces on the system, to go ahead and just analyze Newton's laws, because that's going to give you a block of equations in the X, Y, Z direction, or depending on what coordinates you're using, you can always translate to different coordinate systems. But generally, we write the forces in Cartesian coordinates. It gives you a block of information that you may or may not use based on some other concept, physics, mathematical, calculus, whatever that you're going to use to solve for the system of equations. Analyzing the forces on a system is always a good way, particularly in this class, because it's a mechanics class. Analyzing the forces is always a really great way to start. By analyzing the forces, to apply Newton's first and second law, you're going to have to do some sort of qualitative analysis of the motion to know even which force to use, which also gives you more information about the problem. And the final thing I'll say about the 3 laws is that you will either use the first or the second, depending on the circumstances. But based on the discussion that we had about the 3rd law, if there are forces present, then clearly the 3rd law is always there. We don't necessarily need it, practically speaking, because like pair of forces may be on objects that we're not considering. For example, you asked about pair forces here. These 2 forces are not pair forces. but these two are. Now, when we do this problem, we're not going to analyze the pulley. Why? Because we're only concerned about the motion here, and the pulley is ideal, so it's not contributing to the motion. But when we relax that criteria, we're going to need the mass and the radius of the pulley, so the system won't just be these two objects in tandem by a mass of the string. The system will be these three objects in tandem by a mass of the string. If we were then go on to junior or senior level physics, we got to put the string in there too. We give the string a mass. And so the system becomes 1, 2, 3, and 4, the mass of the string. And that's really what physics is, right? You start with something basic, relax some criteria so you can do the problem. But as you relax that criteria, it gets more complicated. So you need higher order methods to do stuff. And so that's all of what physics is. Same thing over again once you learn the basics, but then with less restrictions and higher order mathematics or processes to actually solve for those complex interactions due to the fact that the restrictions have been lifted. But a fundamental basis, no matter how complex you get from this point on, is if you have a system, one of the first things you should do, if you can do, is figure out what forces are on that system and analyze Newton's laws. That's why everybody says, even Einstein, I think we said that, I stand on the backs of, on the shoulders of, the people who come before me. Well, I can tell you this right now. Even considering Hawking, Einstein, anybody smart person you can think of, the person with the biggest shoulders is Isaac Newton. So that said, let's move forward. To date, and I don't know if anybody's going to kick him off that pedestal. So we're going to let's do a free body diagram for each of the objects before we analyze it. So for block 1, representing the mass as a point particle, I've got 3 forces. The normal force up, the weight down, and the tension force, which we can call T, not T1, but just T, because we've already analyzed qualitatively that's the same as the other guy, to the right. I like to indicate the acceleration, if there is acceleration occurring, I like to indicate that somewhere, on the free body diagram in this FBD. They're going to talk about this in the book. Do not underestimate it. Always write an FBD. So the acceleration in the x direction is one of the unknowns. The system, the things I'm looking for, is in the x direction. But you can also make a note that the acceleration in the y direction is 0. Right? Because we have no motion along the y direction as block 1 moves along the x direction. That's the free body diagram for block 1. For block 2, it's even simpler than that. We've got 2 forces up. I'm sorry, 2 forces on the object. One is up. That's the tension force. And one is down. That's the weight of block 2, M2G. I think I forgot to put the subscript over here. So this is M1. All righty. Any questions before we now apply Newton's laws to each of those free body diagrams and get our system of equations? All right, let's do. So I'll do the sum of the y. So which law applies in the y direction, the first or the second law? Who hasn't responded today? Ratch? How do you pronounce your last name? Ganime? Ganime. Yeah, Ratch. In the y direction, as his object, and look, let's do it here. Here's the y direction, is vertical. Now, when I cause this thing to move, is there any motion or acceleration or even any motion in the y direction?
Yes, because if you draw, if the if because in that well, of the object the box, no, there's no acceleration in the y direction, but
Mm.
it's
going. You're gonna
moving across horizontally because the pulley is going down in the y direction. So there's acceleration in the horizontal direction. I think.
Great answer. Good answer. You think? Yeah, but let's clean up some. So definitely block one is not moving in the y direction, clear in the x direction. But this thing, something, kind of shaky. So let's get to that next. This block definitely not, right? So if that's the case, which law should I apply in the y direction for block one? Now again, the third law always is applicable. Each of these forces have pair forces. They are not pair forces themselves, but the pair forces are somewhere else. We're not talking about that right now, right? Like we're working about just the box. So whenever I ask this question, I'm really asking about the second and the third law. Sorry, the second and the first and the second law. Third law, you don't have to keep repeating because if there are forces anywhere, the third law is obviously applicable. So, and we've applied it by identifying the forces. We don't need to do anything else. The third law can't help us in any other way once that's done. So, between the first and the second, Ratch, which law should I apply for the y direction of box one?
The y direction in box one, I would say the first law.
Yes, awesome. Let's do it. That'll be the first equation. So the net force in the y direction equals 0. Cool. Why 0? Because we said no acceleration along the y direction. But we do have forces. What forces are they? The normal force up and the weight down. So they have to be in opposite directions. So normal force positive minus m1g equals 0 gives us a trivial result, which we would expect since it's a flat surface, that the normal force is equal to m1g. We're done with that. Now, that's all we can do with the normal force right now. When we get friction involved next week, we're gonna definitely need that for other things. I'll just leave that for now and we'll move on. Now, I want to tell you something that came up, which is important. I'm glad you brought it up. I kind of usually wait for some student to say it before I mention it. We clearly have these. Now, we know that the magnitude of the acceleration is the same, but it doesn't really make sense that the direction of the acceleration is the same because it's the same acceleration, right? Meaning this thing is going vertically, this is going horizontally. So it appears that physically they're going in different directions, but they're connected. So I got to be careful how I set the problem up because that's illogical that you could have two objects which have the same acceleration arising from the same force and having the same magnitude of acceleration be accelerating in different directions. There's something a little off about that, a lot off actually. So what I want to offer to you, this is not something that's obvious until you start to get to a class like this, because we kind of take math as such a strong tool. We kind of think that it's the math that dictates things, right? So when we look at a picture like that and we call up the y direction and x and the horizontal direction x, we kind of think, well, the fact that we've defined up as y and horizontal as x is dictating the problem. But in reality, the physical situation has no idea what you're talking about. Like, it doesn't know you're calling up, positive y and down negative y and, the horizontal direction, the x direction. It's just doing its own thing. In fact, I've already started to kind of manipulate the physical situation by calling this an ideal pulley. What if I created a situation where I took block one and swung it back up so it was along a straight line and then had gravity acting along that direction? I can do that not in physical space, but I can do that in mathematical space. I'm going to get the same answer. So what I like to think, the way that I kind of teach doing this, since when I superimpose a coordinate system onto a problem, it's me superimposing a mathematical construct on just so I can analyze it. But it's not dictating anything about the physical situation. It's the other way around. The physical situation is dictating certain circumstances, and I'm simply just trying to explain it and understand it with mathematics. So I better make sure that when I project my mathematics, it's like conversations where people project things and then they, get back what they're projecting. It's the same thing as what I'm trying to say here. We're projecting on a mathematical perception about what this is, X and Y and positive and negative, all that. This thing doesn't know anything about that. So when we do that, we better make sure we project it in such a way to get the thing that we need, that is correct, right? So it is illogical to say that an external force on a system is causing it to accelerate with the same magnitude of acceleration and for the same reason, but then somehow it's causing it to accelerate in a different direction. One, to accelerate part of the system to accelerate in a different direction than the other. For me, that's illogical. Now, you might be able to do that, but it's, there's things complex like different coordinate systems and translating back and stuff like that. But we're not doing that. I guess you could do something like that, but it'd be two different coordinate systems and one here, there. I mean, we don't really need to do that. We're just going to keep it simple with the same coordinate system. And one way to do that is to just think of the coordinate system being translated over the pulley. That is, I call this up, the positive Y direction, this the negative X direction. Since the string is going over the pulley, why can't anything else? It can, right? I just project it over. So down is the positive X direction here, and to my right is the positive Y direction relative to this guy. That's what I teach because it just makes sense to me and it works out. If it works out, it's right. So there's probably other ways you can do it, or you could just fudge it and not say anything about a coordinate system, which I think is what your book does. But I like to address the issue just because I also like to talk about this thing about mathematics too, because it's a nice place to start to introduce this idea that, oh, wait, mathematics is the language of physics, but it's not physics, right? Like when we say things, break the universal laws, usually we make comments like it can't violate the laws of the universe or the laws of physics. We don't say it can't violate the laws of mathematics, right? So just keep that in mind. So that's how I'm going to do this, that we're going to think about this coordinate system being translated over this pulley where here, so that would, everything is tight. It's tight now because that means they're both accelerating in the same direction and it doesn't violate anything else. So if it's right, then it's right. And that's the ultimate test. They even say that in Oppenheimer's movie, right? The ultimate test of any theory is experiment. If you have a theory, you test it, and experiment validates it, then the theory is right. That's the only thing that dictates. Mikey, question.
Here's how I'm visualizing it. I'm not sure if this is like a valid way of thinking about it, so I might as well just share with you. Couldn't you also say that the pulley redirects the coordinate system because it redirects the string or the direction of the string? Because that's how I visualize it now.
Well, it does do that. So you say it redirects it to the Y direction?
Yeah.
What you saying?
Yep.
I guess you could say that. I mean, I guess you could. But yeah, maybe I won't say that's wrong. Armand, question?
Yes. Is the string attached to the Y axis?
No, the Y axis is just some mathematical construct that I'm putting there. It's not attached to anything. No.
So what is the normal force and the M1G force acting?
It's acting on block one. So those forces are moving along with the block.
Oh, so the
And
string is attached to a block?
Yeah, like this is the picture right here. Right here. The strings are attached to both blocks, and the string is what's causing them to pull it over. So can you see this?
Yes.
Can you see this demonstration here?
Yeah. Yes.
Yeah. So that's what this is. Yeah. So definitely, the strings are attached to the blocks.
Okay. Thank you.
So, Mikey, one other follow up on that. You can do what you're saying, but technically, that's a translation. So you have to write one coordinate system in terms of the other, and it's a 90-degree angle. You could do all that. Like that's something that's done. Translations, translational matrices are something that's done in like junior level math and physics. You could do that, and you're right. That's technically what you could say it that way. But this is not. We're not at a level where we're doing all that. So basically, if you said that, how do you match it up? You can't. We've already shown that qualitatively, motion in one direction is very different than motion in the other. So the same thing with the forces. What we're going to ultimately do is equate these things, equate the tensions. So technically, if this is the tension in the x direction and this is the tension in the y direction, you can't equate them. It would be the same thing as putting subscripts on there. You can't do it unless you have a translation. And the translation would be that ty equals minus 90 t whatever. And then you have to do that. I mean, you could just ignore it and just do it anyway. But if you do it anyway, like I just at some point, because I used to do that, because everybody kind of does that. They don't say anything. I don't think your book is going to say anything about this stuff that they're just going to assume it's the same. But I'm just being kind of technical because they're not the same. So this is just one way that you can justify not having to do like a translation between the two axes. That's all. Just one thing that I explained. Does that make sense? What I just said?
Yeah, it does.
Yeah. Armand, is another question, or did you forgot to put your hand
No,
up?
I forgot to put it down.
Okay, cool. All right, cool. Great questions. Great questions. But yeah, you can think of it any way you would. This is the way I do it, and it's all good. As long as we know what's what, whatever, you can do whatever you want. Get the right answer is right. All right. Any other questions before we proceed? And we're gonna stop here. I know we went over the break. We're gonna stop here in a minute. Oh, we're way over the break. But this is foundational. So if you get this, then we're gonna build on it. So I just want to make sure I don't screw it up. Any other questions? All right. So now let's get to the really interesting part, is the X direction over here. So anybody, Arcady, for this guy, for the X direction, first or the second law applies on block 1?
I would say the second law.
Awesome. Got it. Second law. So net force equals mass 1 times, now it would be acceleration 1, but it's not, because we already determined that's the same. And here's what I'm talking about, again, direction. It's also the same thing for acceleration. This would be an AX, then the other guy would be AY. So how do you put them together, right? Like, so anyway, A. Because remember, it's not just magnitude, it's also direction. So if it's a different direction, it's a different direction. That makes a difference. It's not the same vector, right? You gotta match them up somehow. So, but yeah, dealing with magnitudes here, then we'll do sorry. Yeah. We'll do the two forces. Well, it's only one force because there's no friction here. So the only force in the X direction is T. So this becomes T equals M1A. Now, are we equally determined? No. We got two unknowns left, and this is the fourth equation. So we had 1, 2, 3, 4. I promise you we needed 5 equations, and we do. We need one more total equation to get rid of these two unknowns. So where do we go to? Well, we haven't evaluated this block yet, block 2. Which law applies on this guy? The first or the second? Karim. Karim, you there? For block 2, first or second law? Is it accelerating or is it going at no change in motion? Raheem? Arcady, tell me which one, first or second for block 2.
For block 2, second.
Yes, yes.
Okay.
And if you sound like there was a little bit of unsureness in your voice, they're connected and they're clearly moving in tandem. So whatever acceleration this one has, it looks like this guy has the same acceleration, and it does. But we don't know what that is, but it's definitely accelerating, and it's the same acceleration, it seems, and so we're going to go with that. So yeah, so for M2, so this was M1. So for M2, it's the second law. Net force on, and again, it's the X direction, same direction, so we're good with that. So it's going to equal the mass of 2 times the acceleration of 2, and it's the same magnitude and direction, because we handled that already. Now that's got 2 forces on it. So how would I handle the sum of the forces over here, Arcady? Since you're like you got a handle on this, so keep going. When I write out the sum of forces on this guy here for block 2, what should I write? I've got 2 options. So which one is going to be the most consistent option with what I've already done? What are the sum of the forces on block 2?
Wait, can you repeat the question?
Yeah. Yes. So block 2 is this small pod thing, ear pod thing. It's going down. It's accelerating down, we just said. But it's got 2 forces on it. The 2 forces are here, tension and M2G. We've already evaluated the right side. The motion is definitely changing and it has acceleration. We said that. But now we have to evaluate the left side to write out how those forces are contributing to that acceleration in the appropriate way. We have to sum the forces. So in this next step, so over here, I'm still going to have M2A, but over here, I have to write out the individual forces consistent with the appropriate way in which they're superposing on this mass, adding on the mass. How do I write them? What do I write for the left side of this equation?
You can write M1A, maybe.
M2A, yeah, go ahead.
G.
That's what you meant, right? M2A.
Yeah.
Sorry, it's not M2A, it's M2G. So wait a minute.
Yeah.
So I already have the M2A. Maybe that's what you meant. It's already on the left, yeah.
Oh,
But
okay.
I'm on the right side. Yeah, so M2G. I'm assuming that's what you meant. Go for it. What else? Okay, maybe that's not what you meant. Maybe there's some. Anybody else want to try before I clean it up? Or you want to finish if you can? Okay.
I'm a little confused, so I'll just let if anyone else wants to answer it.
Okay, can you articulate what you're confused about?
Like what else we need to write besides the M2G?
Okay, let me help you with that. Because if you have that question, many people do. There's another subtle brilliance about Newton's laws, which is, all I can say is brilliant. Now, it's going to seem obvious once I tell you this, but it's not obvious, one, because you're having difficulty now. And just think about before Newton created Newton's laws. Like, it's not obvious. And here's the thing. It doesn't matter what the heck is going on in any other part of the system. It doesn't matter. It doesn't matter. You can have a gazillion forces on the pulley, on the thing, on the mast, everywhere. It doesn't matter. And we know that all of that stuff is contributing to how this thing is, M2 is moving. But for some reason, the universe works in such a way is that you don't have to worry about any of that. The only thing you need to know about the object you're trying to evaluate relative to its acceleration is the forces that are on that object. And if you get that right, and get that right on every end, in other words, you can have microscopic vision, even if it's a complex system, a gazillion objects, a gazillion things going on each object, you just focus on that, see what the acceleration is on that, add up the forces on that. And if you do that with all the other forces, all the other objects correctly, you're going to get a system of equations that's going to give you right answers for everything. Even though we know inherently and intuitively that even though we have these two forces on them, they're being affected by all this other stuff. But it turns out that whatever forces on there are affected in such a way that the influence of all the other stuff is somehow inherent to those forces. Now, that seems trivial, you know, now that we know, but it's not. It's not trivial, right? If you really think about it and like try to go back and put yourself in Newton's place, that is not trivial at all. And none of what he did with these laws, even though now they seem so easy, again, that's why he's the king, because like it's incredible the insight that this dude had to then write these things down so simply and so practically the way we're using them here. It's incredible. Like it's straight up like influence from something else coming out. I don't know, like it's crazy. Anyway, so then if you do that, when you look at this thing, we know that it's going down. So because we know it's going down, I'm stick with you, Arcady, because I think you're on a precipice here. It's going down. So if I were to ask you, which of these forces is greater than the other? Is M2G greater than T, or is T greater than M2G? Give me an answer and then tell me why, how you know that.
I would say that greater would be, wait, greater? Let me see.
Which force has the largest magnitude?
M2G?
Awesome. Why?
Because it's pulling down.
Yes.
Yeah.
Because the acceleration is down. That's right. It's completely illogical that the thing could be accelerating down, but somehow the tension is greater or force than M2G and there's opposite direction. If that were the case, it'd be going up. And you don't need to know anything about any other part of the system. All you need to do is look at that and know what you're looking at. Now, generally speaking, we write the acceleration so that it's positive, inherently positive. That's what I did back here. Now, it's not so obvious because I only have one force and it just led to this equation right here, equation 5. But like if I had a frictional force that was retarding the motion and is accelerating to the right, in that case, what I would have written was T minus the frictional force. Why? Because clearly the tension force would have been greater than friction. Why? Because the tension force is in the same direction as the acceleration. In fact, that's what Newton's second law actually says. No matter how many forces are on the object, the net force is equal to the mass times the acceleration. Well, the net force is a vector, and mass is not a vector, so the net force gets its vector quality from the acceleration. So even if you have a number of forces in that, all the forces that are in the direction of the acceleration must have the same sign as the acceleration. And since I'm implying that remember I told you I'm imposing the mathematics on the thing. So I'm saying that that direction is the positive x direction and this direction down is the positive x direction. So if I'm saying that the acceleration here is positive x, then it's got to be positive x down here. That's why I was saying I started teaching it this other way as opposed to x and y. Now you can do X and Y, but technically speaking, you'd have to have a translation, and that just makes it more complicated than it really is. And so this is what I do. But now it makes kind of sense. These things are unified. So they have the same magnitude of acceleration, the same direction. And at this point, I know that this force M2G has got to be greater than T because it's causing it to move. It's the force that's causing it to move in that direction. This is trying to make it move in the negative X direction. So when I write that, I'm going to write M2G minus T. Minus T is equal to M2A.
Oh yeah,
If
that
I
makes
were to
sense.
switch, thank you, good. If I were to switch it around, what effectively I would be doing is writing this equation with a negative acceleration and this equation with a positive acceleration, and it would give me an error. Now, another way that books avoid having to have this discussion is they start with putting the axis on this guy, right? And then just say something about the tension over there, just using the absolute value. And that's a little bit easier to kind of see, right? But I avoid this. I avoid doing that because I actually want to have this conversation because I want it, you know, up until now, it probably didn't occur to you, but I want it to occur to you now that whenever we take mathematics and we superimpose it on a situation, we're doing that, right? There are physical laws and there are mathematical laws, but those laws are not the same. And the physical laws are usually the laws that are actually dictating what's happening. And the mathematical laws are just laws that you use in the mathematical tools that you're using to figure out stuff. You know, you got to do it the right way, but it's not, the mathematical laws are not dictating anything about the universe. They're just explaining the things about it. It's kind of like this. Math and physics aren't the same. If you're, I think I gave this, maybe I gave this speech on the first day, but you know, you're at France, you know, whatever, you speak a different language, but you see some people arguing and they're in love and you know love, but you don't know French, right? You might be able to ascertain something about what's going on, particularly if you saw, you know, when you walk by the couple, the guy and the, you know, looked at some other person outside of that couple, you know, you might figure it out. So the point is that the actual ideas like love, honor, dedication, loyalty are different than the words that you're using to describe them. We aren't really in places where we have to think about the difference of the language and the ideas very much until we get to very crucial things like, you know, court of law we were discussing, or court of public opinion and discussing ideas, or maybe a physics class where we really begin to think about the difference. But there is a difference. And when we superpose all this mathematics on this problem, the physics has no idea what you're talking about. It doesn't really care about any of that. So you better make sure you do it in such a way to get the right answers that you know are correct. So I like to do this and talk about this so that you begin to have a sense of that. It's not really necessary to do what I'm doing to get the right answer, but I think it's nice it's a nice place that I found over the years to introduce this idea about the difference in math and physics. So here, everything is all matched up and pretty, right? I've got all the accelerations with the same magnitude and in the same direction, defined in the same way versus positive versus negative, and everything is cool. So now, in the end, I've only got two unknowns and two equations. The two unknowns that are T and A, and the two independent equations are equation 7 and equation 5. So now, what I would like for you to do, and I'm going to go ahead and take a break. We'll take a 15-minute break right now. Maybe 20. Make it a working break. Make 20 minutes. What I want you to do is to go ahead and solve for the analytical solutions. Get the actual values. You know, not get the analytical equations for the things, and we can estimate. Why did I do that? We can actually go ahead and get the numbers too. I can weigh out the masses of these things, and we can actually get an idea of what the numerical value of the acceleration. So the mass of mass the mass of mass 2, we'll do it in grams, we can convert it, is going to go 64 grams. 64 grams. And the box is, no, I can't do that. The box is 61. Let's see. Oh, maybe it is, because it's fairly frictionless, so cool. That's interesting. Yeah, so the M1 is equal to 64.0 grams, and M2 is equal to 61. Is that? No, it's the other way around. So this is 64. And this is 61. You might say, well, you know, why can one pull the other? It's because the table is relatively frictionless, so there's not a whole lot of friction there retarding the motion. So that's why. And it might be a little bit, you know, I've kind of done much of the work here to set this up for you, so let's make it interesting. Once you get that done, I want you to go back and we're going to throw an angle on this. So we're going to do this problem, and you can go ahead and start working on it if you want, where we have this guy. So this is still 1, and this is 2. But now we've got a plane angle here, theta, and we're going to work through and find the tension and the acceleration for that guy. In fact, I should give you an angle. Let's make the angle theta, let's make it small, because with this it might make it so. Let's make the angle theta equals 5 degrees. Now, to get the analytical solution, you don't need a numerical value for theta, but I want you to do the same thing to get the numerical solutions. Keep the same masses there and put into that. And I'm going to do that when we come back, but you know, you might be able to start it if you want. So go ahead and finish this out, get an analytical solution for T and for A, put in the numbers, get the values. And if you finish that and you so desire, go ahead and start working on this, setting this up in the same way we did this, because this is the next problem we're going to do in class for the second half of class. Understood? Any questions, problems, troubles, gripes? All right. Go for it and take 20. So we come back at, I think it's top of the hour now, right? Oh, man. Yeah, okay. So we come back at 15. So we come back at 3:35. Can you hear me, everybody?
Yes, sir. We can hear you.
All right. So we were getting T and tension and acceleration. Well, this is pretty straightforward. We're going to eliminate one of the variables between equations 5 and 7, so that I substitute 5 into 7, then I eliminate T from those two equations, and I can solve for A. So if we do that, we get that M2G minus M1A, goes in directly, equals M2A. And simplifying, we get M1A goes on the other side, we factor out the A, and we're going to have M2G equals A times M1 plus M2, or the acceleration of the system, A, is equal to G, essentially times this normalizing factor. It's a unitless number, right? Because you're going to have M2 over M1 plus M2. So this factor here turns out to be, you know, kilograms over kilograms. It factors out, but it's like it reduces, it's because, it's less than 1 because the denominator is greater than the numerator. So that means that the acceleration A is going to be less than G. And yeah, and that makes, yeah. So we see that another way to look at it is we've got the weight being driven. If I put M2G together, we have the total inertia of the system. That's another way to look at it. That M2G is the only thing that's really driving the system. That the weight down is M2G, and so that's the force on the system. But you're not getting. If it were just M2G, it would be free fall. Like if I cut the string, the weight is M2G. The inertia is M2. But here, you've got that same weight driving the overall system, but it's normalized by the combined weight of all the parts of the system that have mass, your M1 and M2. What we'll see is when we get the pulley, because it's rotating later on, we'll get half the mass of the pulley over there for the inertia. So I kind of think of the numerator as the total inertia of the system, because mass is a measure of inertia. Inertia is resistance to change in motion. So you're dividing the force by the inertia, and that gives you an acceleration. So a couple ways you can think about it. We could put it at the see what that acceleration looks like. We've shown that example several times. So in our case, A is going to be equal to 9.81 meters per second squared times M2, so that's 64, over the sum, so that's 125. And yeah, what we got. Yeah, so it turns out to be about 5.02 meters per second squared is the acceleration of that system. That's pretty realistic, what I showed you there with take a look at it again. So this is what 5 meters per second squared looks like. Approximately. All right. We still got to get the tension. So do that. I like to get, now, of course, you could just take that value, plug it back in here. Sure, we could do that. That's fine. Do that. Of course, do that. But I also want to look at, this is going to be a baseline, these solutions, because as I told you, I also like to consider symmetry with the various problems that we do. So this next problem that we're going to do, I'm taking this problem and placing it at an angle. So we should see that symmetry in the solutions that we get from the acceleration and tension of the next system. Identifying that symmetry, thinking about how, whether it makes sense or not once you get the solution, doing something that we call limiting cases, meaning whatever change I made to this basically gave it a non-zero angle. I should see something about an angle show up in the solution. However, if I reduce that angle to 0 in that solution, that more complex, slightly more complex solution should reduce to this solution for the acceleration, for example. So that's one way that I'm using symmetry in these very simple mechanical systems and solutions that we're coming up with, getting you in accustomed to looking for that, identifying it, understanding it when you see it, doing tests, limiting cases to test for it. That all of that helps your learning ability. So to get the tension, I merely have to take A and plug it into here. And so it's just going to be a constant multiple of equation 10, so that the tension then is going to be equal to the system tension will be equal to G. I like to write it like this: M1, M2 over M1 plus M2. So you can kind of clearly see that if this were unitless, this thing, and now I have units of kilogram, but kilograms times acceleration definitely gives me a force, which is what tension should be. Another way to look at it, again, this is the weight that's driving the system, so we can say that the total force on the system is the weight of gravity of the mass hanging over the edge, so M2 times G. And again, you can think of that weight being normalized by this same factor that normalizes the acceleration. Well, I guess a slightly different factor, but M1 over M1 plus M2. Because here this is M2 over and this is M1 over. But I guess you could flip it, or I could, whatever, but then it would be a different, whatever. Okay, you got it. So there you have it. That's a baseline of how to do blocks on planes, blocks in tandem. You have an infinite number of combinations. You can start putting blocks on top of that and all that. They do stuff like that, but the basic methodology is the same. But you got to practice a little bit. So let's go to a little bit more complex system down here, and let's go with that. But before I move on to that, any questions, problems, troubles, and or gripes about this process?
I got one. How did you go from how did you exactly get T is equal to G times M1 M2 over M1 plus M2?
I substituted equation 10 into equation 5.
Oh, I see. Okay, that makes sense.
And it was a simple substitution, just basically multiplying all that by M1.
Right, okay.
Not going to be that easy in the next one, but that's I like to do this because it clarifies the process is exactly the same, just a little bit more algebra and components to deal with. Anything else? Oh, we didn't actually look at the weight. It's calculated. Basically, I have that acceleration times whatever grams. So it was 64, so 0.064 times that acceleration. So that's about 2.5 newtons, or 3, something like 3 point. Let's see what we get. 0.064, right? 1, 2, 3, yeah. Times, well, 0.3. Sorry, I was off by a factor. So 0.3 newton, 0.321 newton. So not even a newton, very light. So T equals, and keeping the right significant digits to 0.321, technically, newtons. Anything else? All right, let's move it along then. Let's go to this guy. And I'm just going to kind of sketch out the. So we're still using the same axis process that I talked about before. Now, I gave you a hint with the problem the other day is that whenever you have a block on a plane, it's convenient to make the x-axis parallel to the plane. When you do that, the acceleration will just be along, in this case, the x direction. If I didn't do that, I would end up having components of the acceleration that I would have to resolve, and that's just needlessly makes the mathematics a little bit more challenging to deal with. So we don't need to do that. So the general rule is what we do is whenever the block is on a plane, you make the x-axis, you make whatever axis you want, but one axis should be parallel to that plane. Now gravity is still acting straight down. Gravity is the weight is still here. We'll go ahead and put theta up here. We'll make theta 5 degrees. I don't need to have it here. The weight, straight down, mg. Now we can go through and prove the geometry if you want. I'll let you do that. I did it quickly as an exercise. But it turns out that this angle here is going to be the plane angle. The angle that the y-axis makes with the line of action of gravity. Yeah. So what I'm saying, I'll make it a color. I'm saying that's theta, right? Obviously, but this is also theta. I'll leave that to you to maybe work through and convince yourselves if you're not convinced. Which means now I have two components of gravity, one along the y direction. So along this direction here, the negative y direction, I'm going to have mg sine of theta. And along the x direction here, I'm going to have a y component, an x component, which will be mg cosine of theta. That's this guy. I still have the tension force and the normal force. So to the right over here, I've got tension. And straight up, I've got the normal force. Straight up along the y-axis, which is actually perpendicular to the plane. A little messy, but we'll do a free body and clean it up. But that's everything. I've got all the forces resolved. So I've got 4 forces technically, 2 components of gravity, and then the normal force and the weight. So the normal force and the tension. This situation doesn't change. It's still tension up, M2G down. Okay. That's M2G. I think I'm gonna need to go ahead and erase this other stuff over here. Don't mind. You feel there's nothing over there. So M2G there. And tension is up. From this point here. Now, again, I've said it several times, say it again just to remind you. If and when we consider the pulley, third law has these same tension forces here and here, but they won't be the same because of the mass of the pulley will matter when it's not an ideal pulley. And we'll have a T1 on one side and a T2 on the other side. We don't put that here because all the pulley does is redirect the force over the slope of the pulley. It's a little bit tight, but hopefully you can make that out. Let me do a free body diagram over here, both. So the free body diagrams for M1 looks like this. We've got tension there. We've got normal force here, making a 90-degree angle with the horizontal. We've got mg times the, what do we say, sine or cosine? Wow. I'm tired. I spazzed. This is cosine. And the other one is sine. We're doing the vertical angle here. So this is the adjacent side, y-axis. So that's cosine. And this is the opposite up here. So that's sine. But I went back and caught that. That would have been confusing to me. So M2 was oh yeah, okay, this is M1. So M1 G sine theta. M1 M1 times G times sine of theta. That's down the hill. So that's here though. So here, this is M1 G cosine of theta. And this guy is M1G sine of theta. Okay. Now, M2 is simple. And also the acceleration still, in this picture, the acceleration is going in the direction of T2, or of T. Up like that. and no direction along the y-axis. AX, so this is AX, and AY equals 0. And then for this guy, because of the nature that of the forces, T is up and M2G is down. Which one the greater? Well, M2G, why do you know? Because its acceleration is down toward the X direction. So there you have it. You can get the information from the free body diagram to try to set up the system of equations. There. Someone want to give it a shot? Go for the y direction for this guy. And again, as this thing moves up the plane, now actually I should say something. Well, we'll get to that in a minute. But yeah, as it moves up the plane, it's not moving or accelerating along the y direction. So which law would be used for the y direction for block one? The y direction for block one. Anybody? First law or the second law? Our new foe. You wanna give it a stab? Which law applies for the block one on the ramp in the y direction? So what we're talking about is something a little bit more like, it would be like this. Go ahead.
Would it be the first law?
Yes, it's the first law again. Now let's just, before we get into it, this is the problem we just did. I've changed the kind of orientation of the plane, but you know, something pulling the plane over a ledge like that, right? Now what we've done is we've turned it up a little bit like this. So now you still see there could be acceleration, but it's, well, that's more than 5 degrees. That's why I don't want to play around with it. Because now I'm kind of pressing down, but yeah, I still get acceleration, but you can see its acceleration is not as high, which you would expect, right? So we should see that somehow reflected in the final results that we get of the answer there. Okay, so the acceleration you might expect to be less. The tension, what do you expect the tension to do? To get greater or less? What do you think? Greater or less as you move? That's a little bit counterintuitive, I think. Yeah. But we'll see. So just think about those things. So wonderful. Whoever is our new full, yeah. Question, Mikey, question.
Yeah, where exactly is the mg sine and cosine pointing to? Like what angles are they like exactly? Like it's kind of hard to see in the video, so that's why I'm asking.
Yeah, it is. It's a little small. Let me go ahead and blow that up over here. Let me make sure this is clear. Definitely you get this. Tension is here. Normal force is here. Gravity is straight down, hence makes an angle. Straight down. Now, this is theta right here. But look at this. If that's theta, this thing right here is theta's complement. That. But that means that this is also theta's complement there. But I've got a right triangle right here. Right? So that angle has got to be theta, which is this same big angle here. So if that's true, then this angle here is theta. But now the gravity makes a right triangle if you project a perpendicular back from gravity to the y-axis, from the weight of gravity to the y-axis. You've now got a larger right triangle here. It's a similar triangle to the one that I just showed you right here. Right, it's like back up at the, kind of like the angle of that whole triangle. So, but this triangle, the component here is the adjacent side of that right triangle, with that being theta. And so this guy right here is what I'm calling mg times the cosine of theta. It's hard to see down there. And this vector is this guy, this side is actually, so again, mg is that thing. This is the cosine, and this is the sine, and it's pointing in this direction. So I projected it back up to the axis here. And that guy is, so it's the opposite side of that triangle, of this angle. So that's mg times the sine of theta. Does that make sense?
So
Yeah.
mg sine theta is oh geez, how am I supposed to specify this? Like it's pointing to the yeah, geez, I'm not even sure how to like explain like where like I'm still trying to, okay, I get mg where I get where mg cosine theta is pointing to, but like I'm not exactly sure where the sine theta part is.
Okay.
Like the arrow is kind of like a little like,
So this is the right triangle here. Do you see that? I'll blow it up. This is the right triangle here.
Oh, yeah, that one.
Okay, so gravity is straight down. Then mg, so I'm projecting back. So the x-axis, the y-axis does something like this. So I'm going to project back to that axis, so I get a perpendicular, like this thing here. But so that's the long leg. So it's got a gravity points from the center of mass down. So the other legs have to kind of go to the same point. I'm going from this point to that point. And I can either go straight down like that, or I could go along the y-axis first in this direction, and then I can go along the x-axis or the negative x-axis in that direction. So, yeah, so this, if the hypotenuse is mg, and this side is mg cosine of theta, and this side is mg sine of theta, where this angle here is theta. So that's the thing that just brought over here.
I see it now.
Cool. Awesome. Anybody else?
Is the right triangle that's coming down from the center of box one um down in the negative y direction? Does that go below the bottom of the ramp?
Well, let's be careful. Let's be careful. That's one thing that's a little bit confusing when you're first analyzing these things. The force is not in physical space. It has its own. If I were, when I do these force diagrams, this thing over here, it has nothing to do with direction. And the magnitudes of the vectors, are relative to whatever. Like it's like apples and oranges. So like if I were to look at the space and kind of graph the space out, completely different force. So the length of this vector has no relevance on the geometry, the physical geometry of the system at all. But I am superimposing kind of on the same. I mean, I'm really not looking at length here, but there's nothing that I need because once I get the acceleration, that'll take me back to the kinematics and stuff. But right now, as what I said the other day, acceleration is the only quantity that's associated with force. So I'm not really looking at, I guess to answer your questions, I don't know. I didn't specify this size of this thing. And, even if I did, I could have several all similar triangles that are much bigger and much smaller that the same ratio of angle to length. So it could be anything. And this is just, in this case, it's just a little box, but maybe it represents a car on some triangular area that, is seven, whatever, several times larger scaled up. So in that case, maybe the force would go if it's a larger mass relative to, the proportions of the system. So it's really irrelevant. And I don't know the answer to that question. I didn't specify because it doesn't really matter. It's not going to weigh in whenever I evaluate Newton's forces on the system.
Okay, thank
Does that make sense?
Yeah, they're just superimposed on the drawing on the physical situation.
Yes, absolutely. That's all. In fact, I haven't even drawn them to scale because that's technically what you should do with vectors. But because we're not using a graphical method to analyze them, I'm ultimately using an analytical method. Really, this is just a sketch just to keep things straight in my mind so that I apply the laws of motion, the force laws correctly. That's all.
Okay, thank you.
A good question. All these great questions today. All of them. All right. Anything else before we apply the first law to the y direction? Okay. Brassing, I think. It used to happen to my summer class, not so much on anyway, whatever. I'm out of tea. It's cold tea here. Let me erase this. I don't think that's kind of it's kind of small. Over here, so M G and T. Yeah, y direction. So I'll do that over here. Just save some space. So equation 1. So the next in the y direction, this is for M1. Net force in the y direction equals 0 for M1. In the y direction, that's here, I've got up the normal force, so in, down mg cosine theta, so minus mg cosine theta, they're in opposite directions. And there's no change in motion. So even though it moves up the plane, it's not moving along the y direction because of the way I oriented the axis. Actually, that's another really good point to emphasize what I was saying earlier. I could have made the axis like this. I could have made it like that. In which case, when it starts to move up, there's going to be a component of acceleration along the y direction and along the x direction. So clearly, that's telling you that when you superimpose any kind of mathematics on a physical situation, it's just relative to the thing. It's not dictating anything. Because then when I apply the forces with that axis, I've got to have an acceleration in the y direction, but it would be a component because my acceleration now will be at angle theta relative to the x-axis. So I would have it would be like a cosine theta in the x direction and a sine theta in the y direction. And honestly, it becomes a nightmare because I'm going to have sines and cosines on the right too, and it's difficult to uncouple to uncouple the angles and stuff for both sides. So, but that's just illustrating that you get something totally different just by turning the axis at an angle. But in the end, the overall answers have to be the same. The tension should be the same, and the acceleration have to be the same. But you just have much more difficulty getting to it with that axis as opposed to this axis. I don't know why my iPad just spontaneously comes on whenever I have it paused. Or there's something that happens that scared the crap out of me. So yeah, no shade to mathematicians in the room, but in the universe, well, I won't say that. No shade to mathematicians. I'm not a mathematician. I'm just trying to keep up with y'all. But yeah, just that. So you just want to be aware of that's really what you're doing when you superimpose mathematics situation onto a physical situation. It's just, yeah. But whatever. So let's move on. So yeah, so that equals 0. So now look at what it's showing you. It's showing that the normal force has changed. Whereas before the normal force was just equal to mg. Now the normal force is a component of mg. It's only a fraction of mg. What fraction? The cosine of the angle of the plane. And it means that whenever this plane goes to 90 degrees, cosine of 90 is 0, and there is no normal force on the plane of the block. Why? Because the block would just be hanging straight up and down. And it'll move straight up. Like it'd be like it'd be, actually, this is a problem. The next problem we're going to do, something called the Atwood machine, where you have two masses hanging in tandem as opposed to on a ramp. So if you took this thing straight up, that's what it would be. So, and remember, the normal force is here. So as it goes straight up, that force would be like this would be the wall. So it'd be just hanging there. So it wouldn't be pressing against the wall. So that's consistent with that extreme limiting case. And the other extreme is when you take the angle to 0, Well, when the angle is zero, it's on a flat surface, and we just saw that when that's the case, the normal force should be equal to mg. Sure enough, cosine of zero is 1, so when theta is 0, the normal force goes to mg, and we're back to the original problem that we did first. All of the stuff I'm pointing out to you, those are symmetries, right? That's what we mean when we're talking about in physics when we use the word symmetry. Usually, it's not just the simple geometric stuff. It's the symmetry of the physical laws and how they are in terms of and exact in terms of describing things. And it's really interesting because, this idea of an exact science is really a hypothetical. It doesn't exist. No science is exact. Because, all of this, as I told you the other day, is an approximation. But it's like, it's this thing, well, I don't want to get off on a tangent, but like the idea of duality in the universe. Do we really live in a dualistic universe, or does it just seem that way depending on the perspective of which you're watching it? And I think it really influences all these things. Like, really, I do. That seem to be these polar opposites: Republican versus Democrat. No global warming. Is there global warming? I think somehow, on some level, this is a reflection of what we perceive as a dualistic universe. The reason I got on this tangent is because, is there an exact science? Well, yeah, when you look at this, it's exact. You're going to get the exact values. Why? Because the errors are so small, they don't matter. So it's not actually exact. So it's both. And there you got duality again. If you go to a quantum level, that's actually what happened when in the turn of the last century. Newton did this, and you saw he published the Principia. When was it? 1760 something, 1780 something. Okay, so 1700s, right? That physics lasted for 120 years until the late 1890s, when we got instruments that were able to go on a very quantum level. And what we saw is that none of this was right. F does not equal ma. Velocity does not equal distance divided by time. It equals those quantities plus some relativistic error using the speed of light, relativistic terms. Whereas when you go to macroscopic quantities, like this big, massive, 2-gram box, or 64-gram box falling down, at the weight of a 61-gram box at a really slow acceleration, like, that's giving you a speed of, I guess we could calculate the speed. If the acceleration is, what did it do? That's 30 centimeters. So 30 centimeters is 30, 1, 2, 3, 0.03. Yeah. What? 30 centimeters. Sorry, 0.3 meters. 0.3 meters. So if the acceleration is 0.3 meters, and it started from rest, v squared equals v naught squared plus 2a delta x. So 0.3 times a, which was 5, times 2, and the square root of that. So what was the speed of the thing? So 5-ish, so it's 5 something. What did I say, 0.3? 0.3 meters times, got to throw the 2 in there and then take the square root. So the thing was going 1.7 meters per squared after being accelerated through 30 centimeters, that box. So that's a real value close to our, minus some tolerance close to the experiment made. So the point is that's slow compared to the speed of light. So that's 1.7 times 10 to the 0 meters per second squared. Sorry, meters per second, as opposed to 3.0 times 10 to the 8 meters per second. So unimaginably slower. I don't even know how to compare that. And of course, the masses are much heavier. Rest mass of a photon is like, well, rest mass is 0 of photon, but I don't know. The mass of a rest mass of an electron is 10 to the negative 31. And this guy, this what do we say? What did I just say? Massive, 64 grams. So that's 10 to the negative. That's 6. What? 60. I can't do that in my head. 0. So 64 grams. So kilograms is 0.06.
Be 0.64.
0.64 to, yeah, no, point 0.064, right? Not 0.64, 0.064.
I thought it would be 0.6.
It's 1,000. So 64. I mean, I don't know. I'm terrible at 64 divided by 1,000 is 0.06, not 0.6, right? 64 divided by 100 is 0.6.
0.064.
Yeah. So now putting it back into scientific notation, that is 6 times 10 to the negative 6.4 times 10 to the negative 2. Yeah, right?
Yeah.
Okay, kilograms. And so you're comparing basically comparing 6 times 10 to the negative 2 to like an electron, which is 10 to the negative 31. Proton is negative 27. Electron is negative 21. Yeah. So that's what. So there's no way that Newton could. There's no way they could know. You got like something that's 10 to the negative 32 going half the speed of light. The error in using the basic kinematic equation of velocity equals this is humongous. But when you have something really large and small, it's basically 0. So there's no way that they could know that unless they did an experiment. And when they did, all kinds of crazy things are going. Things don't act the way they do here macroscopically. And so they had to invent quantum mechanics and the mechanics of the quantum particle. And so the equations of motion, things like that, they're all different down at that level. So
I just dropped the bar on that though. I just dropped the bar on that on one of my pages, like about how we can use the conic section for that, because I mean equivalently that's just what it is. And I just wrote something about that the other day because somebody asked me in a different class. But actually it works because everything in that nature is like so small. And so when you take in considerations and even in calculus for polar coordinates, it's not necessarily visible on the surface in a unit circle, right? So actually, yeah, it does work. Because like I'm saying, cosine and sine, all of those functions are, they're explicit. The sine of this, all of that data inside of the unit circle is explicit. So they really could find out if they tested correctly. I mean, it's not going to happen overnight, but in respect to quantum mechanics, it could work. That's all.
what is the it you're talking about, referring to?
I'm just saying because
when you say it could work, what is the it?
Right. So as far as the conic section that we have, it's written in polar coordinates. That's the it that I'm talking about. So in respect to quantum mechanics, we actually, it's like they have some formatted mapping, and when you're looking at like the electrons, the protons, where they're at in respect to quantum mechanics, we actually can apply, those same, the same rules of mathematics in a conic section to quantum mechanics. And I just figured that out the other day. And it
Okay.
will work.
Okay, cool. But I think we're talking about two different things.
Oh, my bad.
I'm not talking
I thought you were talking about, no, because I just figured that out the other day and I was like kind of happy about it. Because I don't know if anybody ever discovered it. I don't really I told you I don't look into other people's work or anything like that. When I get something from the Holy Spirit, I throw it out there and I just let it go. So I'm sorry about that. I thought you were talking about like quantum mechanics. I just wanted to touch on that.
Well, I am talking about quantum mechanics. I just think we're talking about two different things. I'm not talking about conic sections. And it sounds to me like what you were saying is a translation of, one unit system to another unit system, perhaps with a quantum problem. But that's not what I'm saying here. What I'm saying is that the reason quantum mechanics had, and you also said mathematical laws, which, okay, I'm not sure what laws you're talking about, but I believe you. I'm not a mathematician. I don't know. I'm not talking about that. What I'm saying is the physical laws that govern kinematic. Now, and of course, basically, we haven't shown it that way yet because I derived the kinematic equations for you all from mathematical equations. But we'll see when we get to friction next week that all of those equations of motion, we didn't really need to take a week or a day. I think I took a whole day to derive all the equations of motion, the general equations of motion, the accelerated motion. I took a day to do that. With Newton's second law, you can literally do it in 5 minutes. So what I'm saying here is that those equations of motion actually come from the force laws that Newton wrote down. And those force laws are considering macroscopic behavior, the behavior of quantum particles when they come together and make big objects that are very slow and very big compared to quantum particles. So that when you take those equations of motion that come out of the force laws and apply them to quantum particles, they don't give you the right answers. You have to come up with a new set of equations. Actually, they're not new. It's just that you have to add on relativistic considerations of the way the universe really works, period, but works on the quantum levels. Approximation of those additions don't really affect, are not obvious when you're looking at big slow particles. When you get down to small fast particles, the difference makes the equations the terms in there that you don't have make a difference, and then they give you wrong answers. So you have to figure out how to add those in. And basically, this symmetry that I'm showing you here is a really good example, because you know how, well, we haven't gotten there yet, but we've gotten here. Like, this is a new geometric equation, right? Because this is a more complex situation than when the angle was flat. But what I told you is whenever you come up with something new to explain something that a theory or an equation previously can't explain, but it's related, the new situation is related somehow to the old situation. When you come up with a new equation, it's got to explain the new thing, but also when you reduce the terms in it that are not in the simpler, in the physics of the simpler phenomena, those more complex solutions have to reduce back to the old thing as well. That's one way how you know that it's probably right. So that's what I'm showing you here. That the normal force in this is a little bit more complex mathematically because I gave it an angle and it changed the normal force on the surface. And it gave me a different equation. But when I put in a limiting case that reduces that angle back to the original, it should also be reflected in the situation. That's what the quantum mechanic does relative to Newtonian mechanics. When you start to look at what velocity actually is, it's going to have a term on it that has the very large, or really they're usually terms that are relating the macroscopic speed to the speed of light. And there might be some other stuff in there depending on the term that you're talking about. But whenever, usually there's a ratio of the speed of the object relative to the speed of light. So if the speed of the object is some fraction of the speed of light, like half the speed of light, then clearly that factor you can't throw out, right? Like V over C is a thing, right? So if V is equal to 1/2 C, then this quantity is 1/2. That's something that you can't throw it out. But when when V is something like 1/100000th of C, well, you put that up there, then you got 1/10000000th. So it's like 1/2 is a whole lot bigger than 1/1000000000. So it's so small, it's not going to contribute to what we call the macroscopic, quantity. So that's, in a nutshell, that's basically the difference between the equations of quantum mechanics and the equations of Newtonian mechanics. All those things are there, but they're just so small that we couldn't see them until we started to measure them. Or maybe, as you, I think, implied, you could see it maybe theoretically. And that's kind of what happened, because Maxwell did theoretically figure the stuff out, but there were other experiments and some other intuitions that were coming from Faraday that he kind of took as well, which were not necessarily experimental, but whatever, observations. But that's a longer discussion. But thanks for the contribution. And I'm not, I don't know what you're doing with that, but you.
Yeah, no, in short, I was
Sounds
just
like
saying
you're
they can
interested.
build a shell. Basically, what I was just saying is they could build a shell model on top of what they already have. So
Okay.
that's the easiest, that's the simplest way for me to put it. Yeah.
I don't know what a shell
That's it.
model is. What is that?
I'm sorry.
I don't know what a shell model is. What is that?
So they could build a shell for it. Like, Canvas is a shell. Did you know that? I mean, just
did not know.
I'm trying to tell you about a computer science shell that you use every day. So Canvas is a shell. That's what it's really called,
Okay.
Canvas shell, right? So as far as, like I said, it's an embed, right? As far as them relationally using these kinetics values for microscopic values, or quantum mechanics. Applicably, they can use it as an embed. They can build a shell for it and testing, and it's gonna work over time.
Okay. Well, yeah, I think we're saying the same. I did say that. Basically, we couldn't figure out, we didn't know that there was a difference until our technology developed to the point where we could start to either actually look at these things on the quantum level or model them on the quantum level using technology, using computers and computer code. And once we started to do that, that's actually how we do that's how we did the experiments. Because like they said in the movie, doesn't matter how smart you are or what kind of theory you come up with, nobody's going to believe you until you test it and the experiment shows it's right. Well, some of these things were so fantastic, they had it initially, and even now it's cheaper to test them, to model them, with code. And so, yeah, that's what you mean. That's what a shell is a computer simulation, code simulation. And yeah, that's exactly how we know. And then so it started to show that a lot of these projections of quantum mechanics were actually right. So that must mean quantum mechanics is right. In addition to the fact that it also reduces back to the Newtonian mechanics when we put in those, relax those quantum stipulations. So yeah.
Dr. Gamble?
Cool. Yes.
I want to know where the
Yes.
where the center of mass 1 and mass 2, there you seem to have a point drawn there. What is that? Like how do you describe that point?
I didn't realize we had gone over. I'm going to keep going here and finish this. So if people need to go, you can go. You can look at finish there, but I'm going to finish and get out and throughout this. It'll probably take me about 15 minutes, maybe 10. But what point are you talking about here? Right here? Right here?
Yeah, any
What point are
point,
you referring to?
the point in the middle of the boxes or the blocks, where the forces are extending
Here?
out of.
Yeah,
Yeah.
that represents the center of mass.
Okay, thank you.
So what we're saying is, first of all, it's a solid object and it's uniform. Well, if it's uniform, it's just like, it's kind of more easy to see it if the geometry matches. So this is a circle, right? If I take a dot, like, kind of like the universe, we say that the universe was a small, point, at some time, and then it expanded. And so, if we take all the universe and put it back in that point, that's what I'm doing. Essentially, that's what we're doing up until a few chapters from now, even though I don't explicitly show that, I just want to remind myself of that. That basically I'm not looking at the shape of any of that. I'm assuming that there's a point particle that represents the mass of the object, and so all of the forces act from that point.
Okay, thank you.
You sure? Because it sounds like that wasn't that was.
It's like it's treated like a particle, right? You know.
Yeah, a point particle is what it's called. Point particle. So it doesn't have a shape or size, but it has all the mass of the particle of the object that you're considering. So it's a hypothetical thing. It's a mathematical, but we don't want to have to worry about rotation or anything, or like you can get into that when you have different shapes and all. It's really just all the problems we do now, even if we don't stress it, which I'm kind of stressing it here by putting the dot. It's just a point particle. 2 point particles are moving along, so we don't have to worry about anything else. That's why I'm doing that. And that's what, generally on the free body diagram, that's what you're representing. That actually has the mass, that's mass 2, and this point particle is mass 1. And we draw the forces from that point. Good?
Yes.
Okay. All right, let's crank this out. So what about the x-axis? I'm going to move it along for you. So I suppose it kind of encouraging you all to participate so we can get out of here. But the block, it's going now here. Another thing I need to point out right here. In this problem, I think I chose the numbers and the angle small enough so that it actually goes down the plane. It continued to do that. I was at about 5 angles, maybe a little bit more. But it's conceivable that if I keep raising this, I'm going to get to a point where it doesn't accelerate at all. Or a point where it actually might accelerate, the system might accelerate backwards. Again, the brilliance of Newton's laws is that, well, it's not going to affect the equations at all. And again, there's with math and physics are different. It doesn't matter what equations I have here, they're going to be right. But given the numbers, I could be at a place where, and also this is not, well, ideally, if it's frictionless, there's going to be a place where it stops, just balances, and then goes to the, if I increase it even more, it's going to start to go backwards. If I put friction on, there's going to be a range of angles where that doesn't move. And we'll talk about that a little bit more as we move on, when we get friction next week. And so that's really what we're dealing with is friction. But a frictionless thing. So there's a range of angles, not just one specific angle where it stops and then above or below that, it basically would be an unstable equilibrium. And we could prove that with certain things that we'll get into later. Anyway, so when you put in the numbers, if it actually is an acceleration backwards in the same equation, it's going to tell you, it's going to give you a negative acceleration. So it's telling you that the angle is going so high that it goes backward. So you don't really have to do anything different. All you got to do is stick to your guns. Make a choice. Like if I choose that the acceleration is going up, which I'm going to continue to choose the same, that's what I've already done. Assuming that it goes up, then if I'm wrong, and the tension either way will be the same. Right. So, yeah, so let's go for it. So let's say that it's going up. So here, I'm going to assume positive acceleration on block 1 up the plane, which means that even though now I have 2 forces, the tension force has got to be greater than mg sine theta if in fact the acceleration is up the plane. So if I write that as a positive acceleration, I've got to write t minus mg sine theta as opposed to the other way around. And by the way, whenever we don't put a sign, it's implied that the thing is positive. If you're saying it's negative, do not make it inherently negative. Make it explicitly negative and put the negative sign. In other words, I could write this equation mg sine theta minus t equals a minus ax. I could do that. That's the same thing. But if I'm going to define the acceleration as down the plane, then or if I'm assigning the acceleration of the plane and I say that this force is greater, then that means I'm implying that it's the negative direction of that force. So I have to put in the minus sign. All right, but we don't. The convention is if it's positive, try to write it as positive. That's what I do, and that's what most people teach. So in the y direction for M1, continuing here, we're going to get the net force in the x direction equals M1A. Okay, but now as I said, the sum of the forces, we'll keep this going. Equation 4. So equation 5, T minus M1G sine theta equals M1A. Okay? So now there we're back to two unknowns, T and A. But now we got to go over to block 2 because we've exhausted everything else. We've done all the sum of the forces on this guy. It gave us a normal force and an equation with two unknowns. So we got to go over to this guy to get the other guy, to get the other thing. And that's the same as it was before. That's going to be, again, net force on, on block 2 in the x direction equals M2A. And so that's just going to be, M2G minus T equals M2A. Okay, so it's these two equations, equations 5 and 6 that we have to solve simultaneously. Now, a little bit of tricks in linear algebra. I'm looking at this, and I see a plus t here and a minus t here. If I add the two equations, I eliminate t. So that's an easy thing for me to do, so I'm going to do it. So equation 5, plus equation 6 is what I'm doing. So equation 7, I'm going to get M2. So if I'm add them, the t's are going to cancel. I'm going to get plus M2g minus M1g sine theta. And on the right side, I have M1a plus M2a. So that's going to be M2g minus M1g sine theta equals M1a plus M2a. So M1a plus M2a. So that gives me over here a M1 plus M2. Again, I'm seeing the same thing that I saw before. Acceleration times the inertia of the system. Over here, I can factor out a G. So I'm going to have G times quantity, M2 minus M1 minus M1 sine theta, because I factored out the G. Sine theta. Now solving for A equals G times M2 minus M1 sine theta divided by M1 plus M2. Now, check this out. This is my solution when I put on the angle. This guy was my solution when I had it on when the angle was 0. A equals G times, it was just M2 over M1 plus M2. Now look at the symmetry here. We said that the acceleration should be less than it was the last time because we put on the ramp. We could intuitively see that. Well, this equation is telling you that. Don't you see the original acceleration is embedded in that solution, the M2 over that. But, so here I have M2, and everything, the denominator is still the total inertia of the system. So it's normalizing the, in a way. But the numerator is kind of dictating the force, right? The M2 times G. So I'm subtracting the weight in GM2 by this other term, GM1 minus sine theta. Some term that has to do, what is it? It's the mg sine theta, the amount of the block on the surface that's pulling away, that's taking away from the acceleration. Acceleration in that direction, mg sine theta is in the opposite direction. So you can see m1g sine theta, I'm subtracting that from the original weight M2G that was there when the thing was 0. That's one way to see it, to think about it. The other way is just math, that's physically. But mathematically, just put in the numbers. When theta becomes 0, then I get sine of 0 is 0, and that term goes out, and I'm back to the solution. Actually, I messed up, didn't I? Did I? I did mess up. No, didn't I? Did I? No, I didn't mess up. There's a minus sign there. Minus. Yeah. Should be minus. Yeah. Yeah. Okay. Um. So I would challenge you to go ahead and get the other solution. I'll let you go. I can do it here in class if you want to stay. But to get t, not once you have that value, you can just take that acceleration and plug it back into any one of these, either 5 or 6. What I like to do is actually compare the tension as well. And so to do that, you would equation 9 here again, plug it back into either one. I usually do this guy here, and then solve for t. I can do it here right now. I can start as you're going. But I was looking at the limiting cases. I was just looking at this, and when the angle is 0, this whole term goes out. I'm back here. But also, when the angle is 90 degrees, it seems like you should get g as the acceleration. But that's why I thought, did I miss a minus sign? Because it's definitely going to be, the acceleration should just be less than what it was. But anyway, like sine of 90 is 1. And so I'm getting M2 minus M1. But if I had, is that a negative angle? The sine of negative 90 would give me positive, and then I would have M1 plus M2 over M1 plus M2. That would cancel, and then A would be equal to G, which is, no, that's not, no, it's right. This is right, because it's the Atwood machine. It doesn't reduce the G, it reduces the Atwood machine. That's right. So yeah, you can't see that, but it should be, if this is 90 degrees, then we have M2 minus M1 over M1 plus M2, and that's what we should have, because you got the masses hanging. It's not free fall motion. You still got the other mass hanging on the other side. So that's cool. That's cool. I may, I'm going to do that with machine for you at some point. Maybe I'll do it over the weekend and post it. And I want to get this stuff. I definitely want to get the friction at the beginning of the week next week. So I want to have a lot of examples here that I've got in my book that it might be nice for you to work through or take a look at. And so I can post some of those posts and give you an opportunity. But like, I'll go ahead and do the tension here. And I just erased the equation, so I don't remember what it is now. Can someone tell me one of the tension equations? I guess I could look at it. It's going to be, I could do, well, the easiest one would be M2G minus T equals M2A. Yeah, that's the easiest one. So now I got to plug this A back into here. So if we do that, M2, in fact, if I take this over and multiply it with the minus sign, I have T is equal to M2G minus M2A. But then A is all this stuff, which is G times M2 minus M1 sine theta over M1 plus M2. Now what I'm going to do is factor out the G. I'm trying to do this quickly and hope I don't mess up. Factor out the G. So I've got T is equal to G times all this stuff that's going to be in here. Now I gotta do the denominator stuff, the common denominator. The common denominator is M1 plus M2. So I'm going to have basically M1 plus M2, but then I gotta, the G is factored out, so I have M1 plus 2 times over M1 plus M2 over M1 plus 2 on that term. So two terms are going to kick out of that. I'm going to get an M1 M2 plus M2 squared, and then minus M2 times these terms. So minus M2 squared, minus and minus is a plus M1 M2 theta. Okay? Now, that guy cancels that guy. So now I have an M1 M2 plus an M1 M2 sign. So I can effectively factor out, and of course the denominator goes through all the terms as well. So I can an M1 2 over M1 plus M2 out of both terms, this term and that term. And if I do that, I get that the tension is equal to G, and I like to write it like this because it's easier to compare it to the last tension. You're going to get an M1 over M2 divided by M1 over divided by M1 plus M2, which is what we got for the first tension. But I still got this term on the outside over here, which is a 1 minus sine theta. Right? Because when you multiply that back through, you get that thing. And that's really cool because, again, you can look at the angle. When sine of 0, when theta is 0 and it's flat, sine of 0 is 0. That just reduces to 1, and I'm back to the tension I had before. When sine is greater than, when the angle is greater than 0, then actually that's saying the tension is less. The tension is less as well. That's counterintuitive to me. That when I raise this, the tension is less than when it's really? Oh, that's because I screwed up. This is a plus sign here. Okay, sorry. Okay, there you go. Yeah. So that's actually a really good point. I almost messed up again. I messed up last week. Because, when I raised this, we did the experiment, the acceleration should get, like, you want to kind of match your, because sometimes things are counterintuitive, and the mathematics give you things that you don't expect. That happens a lot in physics as well. But this is pretty simple. So, like, you can see it, right? Like, that's the acceleration when it's like that. But if I raise it just a little bit, let me raise it a little bit more. But yeah, clearly I got to get up. So yeah, it's definitely, the acceleration is less, right? Now there's friction on that, so it's not ideal. But if it weren't frictionless, it's really nice to see this with force tables and things, which I don't have, but we have them at school. But the acceleration gets less. But you would imagine, and I've erased the picture, but when I put it on the angle, there's now a component of the weight down, down the plane, but the weight that's hanging stays the same. So it's kind of like, when it's flat, there's nothing retarding the motion in the opposite direction along the x direction. But when you start to raise it, now you get more and more of a component of the weight down the plane. So clearly, it's going to be stretching the string, because I still got M2G here, but over here now I got that M1G sine theta. So they're in opposite directions, and so the larger the angle gets, the more that M1G sine theta gets. So you would expect that the tension would get larger. And sure enough, you can see it right here, because I'm adding that M1G sine theta. You can't really see because I factored it out, but clearly you can see that as the angle increases, this number 1 plus sine theta clearly increases. So you're multiplying that factor times this, so the whole thing increases. And it's the maximum when sine of 90, you get 1. So basically what it's saying is that when you raise, if I were to raise the angle up to 90 degrees, so that the masses are basically hanging on a pulley like that, whatever the tension was in the rope, whenever it was a flat surface like this, and the one thing was hanging over, whatever the tension was there, this tension is twice as much. You can say get all of that just from looking at the limiting case. And that's what we talk about as symmetry. Is that we want to see those kinds of behaviors in the mathematics that describes the physical situation as we tweak the physical situation.
Is
Cool.
W2, Dr. Gamble, is W2
Yes.
mass 2 times gravity?
Where are you seeing W2?
In the
Oh, these are
equation for
M's. These are M's. Let me number them. So 9, 10, sorry, 11, 12, and this is 13. So which equation?
13.
So all these things are M's. Sorry, I know it might look kind of like a W. So M1 times M2, and then M1 plus M2. Those aren't W's, those are M's. Is that what you're asking
And
about?
yes, and that's multiplied with 1 plus sine theta.
Yeah, because I factored out. So here I have an M1, M2. I factored out, I leave a 1. Here I have an M1, M2 sine theta. I factor that out, I leave sine theta. But I can also factor out the M1 plus M2 from both terms because it's on all of them. So I'm really factoring out M1, M2 over M1 plus M2. And what's left is 1 plus sine theta. When you multiply this term back through this, you get this.
Okay, I see.
Yeah, so I just simplified it like this because it's easier to see, to compare it to this guy whenever I have it in this form. For me anyway. Some people might not need to do that. They probably could do it here, but I can't see that. I have to kind of get it in the simple form so I can see that this is the original tension when it was just flat, but now this whole thing is the tension when I put it at, at an angle like that. You understand what I'm trying to say?
Yeah.
Hello?
Yes, can you hear me?
I can now, but if you said something when I
Yeah,
asked it.
I understand.
Okay, cool. Whew. All right, well, that's all I got for you today. Thanks for your contribution, and yeah.